Creo que hay Andrés.
Ah, doctor Andrés.
Es uno bueno, ¿no?
Sí, alto delgado.
Con lentes ya. Ese ve si. Mira, a ver si te muestro aquí en la.
Ah, sí, sí. Sí, profesor Andrés. Cubrebocas.
¿Es esta de la NASA o está de NASA?
Ah, sí.
Pero por eso por el frío, porque sí, la verdad se cubre muy bien con el peso. Con el catezazo. Fíjate, no se me ha ocurrido, aunque también podemos comprar cosas en Italia.
Oh, sí.
Si tienes algún problema, Wendy, o si le quieres algo también, tú dime. De hecho, yo proponer que se van a comprar unos pizzas de la vecina. Empiezo a ver, pero el problema es que empezó a ver servicio a partir de las 2. Entonces van a tardar en llegar. Sí, por eso, pero
One question, do you have here in this room a wireless connection?
Yes, there is a wireless connection. ¿Tienes la clave de internet o puedes conseguirla?
La de Vivo, la de WhatsApp, antes sí, me la sé de WhatsApp.
A ver,
Pero la interna no.
a ver, esa es la de WhatsApp estudiantes. No sé si se la pueden hacer.
I don't need really the connection, but I would need to simply see it in order to activate the license.
Okay.
Because otherwise the license is just over the IP port. It doesn't find an internet license.
Toma este. Pero la señal es muy bajita acá.
Ah, ya.
No es mucho que se la... No, de internet.
Me está pidiendo.
Es que esa es por... Sí, y es que esta tiene muy baja intensidad. A ver, déjame ver si puedo conseguir con el trabajador.
They tell me that this is the right. Can I connect with my computer to the screen because I have inputs which I would like to show you in the course.
I think that we can do. Ah, ok. Vamos a necesitar más claves para los invitados y presentadores. El doctor Costa necesita también internet.
Sí, yo tengo esto funciona, no hay problema. Unas días. Hola, buenos días. Eso funciona aquí. Yo no necesito el internet, solamente necesito una conexión para una licencia.
Ah, ok, ok.
Si esto,
Ya le di la...
Ah, ya.
ya, ok.
Ahorita se la...
Pues yo creo que ya.
8:59.
Mira, el cuarto. Ponerte ahora sí está como profesor. Lo que yo confirmado, ahora ya te comprometí.
Yo voy a presentar aquí a los músicos. Primero, hola, presentó el profesor Yair Villador, aquí de la facultad. Todos saben.
Sí, aquí está.
Estamos a la orden.
Lo voy a...
Yo creo que sí, ¿no?
El primero de no, muchas gracias. Ya nos ha graduado varios estudiantes. Hay muchos canciones. Y así.
Cuando te ves.
¿Quién lleva la mesa?
¿Tú aquí?
¿Te ves entiendo? Ahora sí, sonríe.
En esta
Y él sabe lo que es el frío y se ha venido para acá. Yo soy pescado. ¿No? Sí,
se fue para allá.
Entonces, no se conectó todavía.
Claro, sí, entiendo, sí, claro. No, sí, de verdad.
Pongo el video. Pongo el video.
No,
Pongo el video.
el video sí no se conecta.
No, ese no es un oficial, también lo preparé en agua. Pero tal vez un poquito no lo entiendo, no dejamos en España.
Yes.
morning to everyone. So I would like to invite everyone to the opening of second international conference on trends and electronics and health informatics. I am delighted to take an opportunity to introduce our chief guest for this morning, Dr. Ignacio Martinez Laguna, Vice Chancellor for Research and Graduate Studies, Meritorious Autonomous University of Puebla. Dr. Palomino Ovando, Head of the Physical and Mathematical Sciences College, Meritorious Autonomous University of Puebla. Dr. Gerardo Lugo, researcher at University de Montreal and member of steering committee. Dr. Mufti Mohammed, researcher at Nottingham Trent University and member of the steering committee.
He's having issues trying to connect to the internet, but he's sent a video, so we're gonna play the video.
Okay. So we are going to play the welcome notes from the Dr. Mufti Mohammed. So for it's from Research Nottingham Trent University and member of steering committee.
Morning, everyone. I am Dr. Welcoming you all. Welcoming you all to the conference on trends in electronics and electronics. In short, and here with us, we have the distinguished guests, Dr. Ignacio Martinez, Vice Chancellor of Research and Graduate Studies, Professor Martha Palomino Ovando, the head of the Physical and Mathematical Sciences College, Meritorious Autonomous University of Puebla. Dr. Gerardo Lugo, researcher at the University of Montreal and member of the steering committee. Now, allow me to introduce the TEHI as a conference to you all. Now, TEHI, the conference focuses on the experimental aspects of innovations. Electronics and healthcare informatics have emerged in the health domain, providing extremely wide variety of solutions using computers. Healthcare informatics is a spectrum of diverse fields of study of design, development, and applications of computational techniques to improve healthcare. In the academia, medical informatics research focuses on applications of artificial intelligence in healthcare and designing medical devices based on embedded systems. Medical informatics also includes modern applications of neuroinformatics and cognitive informatics in the fields of brain mapping and in the theoretical fields such as computer engineering, software engineering, bioinspired computing, theoretical computer science, data science, autonomic computing, and behavioral informatics, along with electronics, researchers are working to provide substantial solutions in the field of medical informatics for treatment. Therefore, this TEHI conference aims to provide an opportunity to gather all these researchers, scholars, and experts from the academia and the industry working in the fields of basic and applied sciences, engineering, and technology to share their findings. Now, this conference has been planned by a set of like-minded people who want really to all these things to advance for the betterment of humanity. Now, all these topics and the context that I just described have been summarized in 4 different tracks and have been used in this conference. So the first track is the artificial intelligence of computing. The second track is behavioral informatics. The third track is the IoT and data analytics. And the fourth track is electronics. So all these 4 tracks, they have brought together a very rich program that will very soon be shared by our program chair colleague. And it will provide exchange of information and ideas at an unprecedented level. And also we'll have a number of world-leading scientists, professors, academicians who would be delivering keynote talks and interview talks at the conference. So with all these, I would like to thank the local host, the Meritorious Autonomous University of Puebla, for their willingness and their unconditional support to this conference. Without their generous support and sponsorship, this conference would not have been possible. In addition, we have other sponsors here within the conference. We have technically and scientifically have contributed to the conference as well, starting with the International Institute of Invincible Rhythm, who are the main sponsoring body of the conference. And then we have the Mexican Society of Physical Medicine at the Puebla section. We have the SPIE Spring chapter at the Puebla Autonomous University, the IEEE, and the Space Sentinel company, which aims in developing products for the community. So with all this, I would like to thank you all for contributing to the conference. Yeah, all the organizing committee members, all the technical program committee members, all the local organizing committee members who have put a lot of effort in making this conference successful. So I would like to thank you all again and hope that you will be enjoying the next 3 days in a vibrant environment of Puebla. I would like to apologize that I couldn't make it to Puebla to attend the conference in person. That is what was the plan. Unfortunately, due to some follow-up travel plans, my passport got stuck with an embassy for visa, and I couldn't really have it back from there to come to Puebla. However, well, I would like to say that in the future, if there are other opportunities, we definitely like to be with Autonomous University of Puebla, and then we would like to strengthen this partnership and have future events together. With this, I would like to thank you all again and enjoy the conference. Thank you very much.
Thank you, Dr. Mufti Mohammed. Next, I would like to invite Dr. Enardo Luego for give the welcome address.
Good morning, good afternoon, and good evening, wherever you are on this planet. My name is Eduardo Lugo. I'm a member of the steering committee of TEHI 2022, and I'm also part of the technical program committee chair. And organizing a conference is not a simple task. It requires a lot of effort, planning, meetings, and discussions. But TEHI is in a special case because it's a little bit more complicated. And it's complicated because it focuses on experimental, theoretical, and applicable aspects of innovations in healthcare, informatics, biomedical, artificial intelligence, and electronics. The conference always aims to provide an opportunity to gather researchers, scholars, and experts from academia and industry working in streams of basic and applied science, engineering, and technology to share their research findings. Not to mention that it runs very close to Christmas, which makes it even more difficult to do it, okay? What you should expect from TEHI, as Mahdi mentioned, there are 4 tracks, artificial intelligence and soft computing, that we have 9 works. Track 2, healthcare informatics with 11 works. We have track 3, IoT and data analytics with 8 works, and track 4, electronics with 7 works. Some statistics from the conference: 73 authors submit their work and 142 co-authors. 71 submitted papers and only 55 accepted papers. Mostly the works are coming from obviously Mexico, Bangladesh, Russia, Canada, India, UK, Japan, Brazil, and the United States. We have 5 fantastic keynote speakers. Professor Salvador Venegas from Tecnológico de Monterrey, who's going to talk about quantum computing. Then we have Dr. Kazuya Misayan from a company called Sage Sentinel. It's a Japanese-Canadian initiative, who is going to talk about preventive age tech. Professor Elias Manjarres from UAP, Mexico. He's a very well-known neuroscientist. He's going to talk about augmenting effects in the brain. It's a really nice talk. Professor David Brown from Nottingham University in UK. He's going to enlighten us with a beautiful talk on machine learning and autism and learning disabilities and how to help them using these technologies. Finally, Professor Andreas Koster from Simvestat, Mexico. He's going to give a talk on simple magnetic superatom, although there's nothing simple, but that's the way you mention it. Then we have another 4 invited talks from Roberto Giovanni Ramirez from UNAM. He's going to talk about a novel bioimpedance soft sensor using machine learning too. Dr. Héctor Cerecedo from Universidad Veracruzana in Mexico. He's an expert in biophotonics. He also is going to give a workshop. Dr. Kanu Wadira from the Indian Institute of Information Technology, UNA in India. She's going to talk about the next generation Internet of Healthcare Things. Finally, Professor Jorge Castro from the National Institute of Astrophysics, Optics, and Electronics in Mexico. He's going to talk about artificial intelligence, Raman spectroscopy to detect chronic degenerative diseases. The 2 workshops, I really encourage all of you to attend. One from Professor Koster, it's about quantum chemistry and its implementation. It's a hands-on course. And the second one is from Dr. Cerecedo. It's about fundamental of optics and photonics with the focus on biofilms, right? So, well, as a member of the technical program chair, we welcome you again to this beautiful city of Puebla in Mexico, and we hope you enjoy the program the same way we did when we designed it. Thank you very much.
Thank you so much, Dr. Gerardo Lugo. Next, I would like to invite Professor Marta Palavino Ovando.
I want to thank the organizing committee for their kind invitation. I am grateful to the research challenger for research, Dr. Ignacio Martinez Laguna, for his attendance at this event. To our college, Dr. Eduardo Lugo Arce, who promoted our hosting of such an important event. And also Dr. Mufi Mahmoud for organizing the second international conference on trends in electronics and health informatics. The Autonomous University of Puebla and the Faculty of Physics and Mathematical Science is honored to be in the presence of the outstanding researchers who have come to this event. In these coming days, you will learn about experimental and theoretical aspects of innovation and healthcare, biomedical, artificial intelligence, and electronics. You will also learn about developments and application of computational techniques to improve healthcare. All this from international learning experts. You will listen to lectures on various topics, discussion among collective exchange of ideas, and presentation of papers by students. These will be intense days where participants will enjoy a unique experience. We want to recognize the committed effort to make this event possible. We are grateful for the support of the institution and its authorities. Dr. Lilia Cedillo Ramirez, Rector, and Dr. Ignacio Martinez Laguna, Vice Challenger of Research and Graduate Students. We wish our guests a productive stage in the field welcome in our community. We hope that many new connections and collaboration develop out of our participation here together. May the results of these days be an excellent conclusion of many hours of work and the starting points for new projects. Thank you very much.
Thank you so much, Professor Marta Palavino. Next, I would like to invite Dr. Ignacio Martinez Laguna, Vice Chancellor for Research and Graduate Studies, Meritorious Autonomous University of Puebla, to opening of the event.
Muy buenos días a todos y todos. First, my apologies to the non-Spanish speakers and attendants because I didn't prepare my speech in English. Sorry about that. En nombre de la doctora Lilia Cedillo, rectora de la Benemérita Universidad Autónoma de Puebla, le damos la más cordial de las bienvenidas a todos y a todas a esta segunda conferencia internacional sobre tendencias en electrónica e informática de la salud. Saludamos en nombre de nuestra benemérita institución a los invitados del panel de honor. En primer lugar, la doctora Marta Palomino Ovando, directora de nuestra Facultad de Ciencias Físico-Matemáticas, el doctor Eduardo Lugo Arce, de la Universidad de Montreal, y que nos honra con su visita en nuestra institución para compartir sus experiencias. Por supuesto, al profesor Mufi Mahmoud, con Nottingham Trent University, y muchas gracias, doctor, por moderar esta sesión. Por supuesto, con especial afecto a toda la comunidad académica y estudiantil involucrada tanto en la organización como quienes exponen, reflexionan y modelan el contenido académico en soluciones tangibles. Celebramos este macroevento que se enfoca en aspectos experimentales, teóricos y aplicables de las innovaciones en salud, biomédica, inteligencia artificial y electrónica. Desde el vasto programa que se presenta en estos 3 días de trabajo, podemos constatar el cúmulo de resultados y experiencias que se exponen a la comunidad científica en estos importantes campos disciplinares. Este es un claro ejemplo cómo desde la investigación inter y transdisciplinar se puede generar un conocimiento con una gran aplicación inmediata al bien común y universal. Desde la inteligencia artificial, la computación blanda, informática sanitaria, Internet de las cosas, análisis de datos, a la electrónica. En el mundo académico, la investigación en informática médica se centra en las aplicaciones de la inteligencia artificial en el cuidado de la salud y en el diseño de dispositivos médicos basados en sistemas integrados. Desde la visión de nuestro plan de desarrollo institucional podemos enmarcar la participación de nuestra comunidad universitaria en el modelo de investigación abierta y comprometida que se impulsa en esta gestión de la rectora doctora María Lidia Cedillo Ramírez y que busca implementar un sistema institucional de investigación a demanda con óptimo aprovechamiento de las capacidades e infraestructura de ciencia e innovación. La ciencia mejora la capacidad de análisis de los sujetos y potencia sus recursos para modificar el entorno, contribuyendo a generar progreso y calidad en prácticamente todas las actividades del ser humano como individuo y como comunidad. Tomando como punto de partida el hecho de que la UAP se desarrollan actividades científicas, tecnológicas, humanísticas y sociales de alto nivel, se considera que existen posibilidades para fortalecer la investigación inter, multi y transdisciplinaria, al tiempo de propiciar la participación de docentes, investigadoras e investigadores en formación y estudiantes. Innovación sostenible y de elevados beneficios sociales, social, todo aquello que afecte a los seres humanos, sea de naturaleza física, económica, de salud, ecológica. Más que agregar, invito, por favor. Hoy, 7 de diciembre de 2022, en nombre de nuestra organización, el comité organizador y los asistentes de esta segunda conferencia internacional de tendencias en electrónica e informática de la salud 2022, formalmente inauguradas las actividades de intercambio de experiencias, saberes entre toda la comunidad de nuestros países y para el beneficio de nuestras sociedades. Felicidades a todos y que todos sean éxitos.
Thank you so much, Dr. Ignacio Martinez. Once again, I would like to invite everyone to the second international conference on trends in electronics and health informatics. I hope everyone enjoyed the presentation and also the talks, and I believe everyone can have a very good time in this conference. Thank you so much, everyone.
El doctor Salvador no se ha conectado. El doctor Salvador. Doctor Salvador.
Now, 5 minutes of break, and then we begin the conference.
Zoom.
No sé.
No sabríamos.
Conéctense a Zoom, por favor, ¿no? Para que chequen si se
sí se va escuchando.
Ahorita pitaban abajo. Cuando pasó el doctor Lugo, no sé si se desconectó el audio, entonces ya no.
Ah, no, es que se alejan el micrófono. Entonces se tienen que acercar el micrófono, nada más díganles, para que se escuche. Porque ponen el micrófono acá, entonces no se oye nada por eso. Es más que nada por eso. El doctor Venegas no saben si va a dar plática. Porque no se ha conectado. No, no aparece el doctor Venegas.
No hay nadie ahí conectado. ¿Dónde está la liga?
No la subieron.
No la subieron.
No, nada más está conectado Shamin Kaiser, Tanu y yo. Y yo de hecho me conecté para estar viendo cómo se ve aquí en Zoom. Pero el doctor Venegas no se ha conectado. No sé si mandó video.
No.
Es en línea. Ujú. No, ya no. Ahorita le van a marcar. Porque es el que sigue, ¿no? Es virtual, pero es el que sigue. De 9:30 a 10:10. Está en YouTube. Estamos en YouTube en vivo. Es la página de la web. No, ahorita estamos tratando de localizar al doctor Venegas, porque no se ha conectado.
Pero de lo del Zoom.
No, nada. Que checaran si se escuchaba bien. Ya se conectó el doctor Venegas. A ver, déjenme hablo con él.
Hola, muy buenos días. Es que no podía quitar el mute.
Hola doctor. Buenos días. Ya estamos aquí. Ahorita dimos 5 minutos de receso mientras vamos probando la conexión. Ahorita le doy entrada.
Muchas gracias.
A ver, ahorita le comparto. Lo estoy haciendo co-host para que pueda compartir su pantalla.
Sí.
Listo. Si quiere compartir su cámara.
Sí, permítame un momento, por favor.
Sí. Listo, ya lo vemos.
Show screen. Permítame un instante.
Sí. Ya lo estamos viendo, ya.
Ok, y ahí está. la presentación, ¿la pueden ver?
Sí, sí la vemos.
Ok, excelente. Pues ya estamos listos. Entonces tengo hasta las 10:10, ¿verdad?
Sí, hasta las 10:10.
Ok,
El
perfecto.
micrófono para que se escuche.
Muy bien, ¿me escuchan bien?
Sí. Sí, se escucha bien. Ahorita vamos a
Ok, excelente. Pues
Vamos a hacer.
cuando ustedes deciden.
Sí, gracias. A ver, le voy vamos a hacer nada más una prueba de sonido. A ver ahí. Ahí estamos. Ya, cuando ustedes digan,
Un momentito.
El doctor Salvador ya está en línea. Está en el grupo. Es que. Ok. Sí. La doctora. Y aquí en YouTube, la página de Facebook de la facultad, van a videos en vivo y ahí tiene que aparecer. Sí. A ver, muévele. Es con el más y menos. Listo, listo, Salvador, doctor Salvador, cuando guste.
Sí, adelante. ¿Ya comienzo a hablar?
Listo ahí, doctor, lo escuchamos.
Ok. Well, good morning,
Lo van a
everyone.
presentar, ¿no? Lo van a presentar el doctor y ahorita ya puede
Ok,
iniciar.
excelente. Muchísimas gracias.
Nada más lo van a presentar, doctor, y ahorita.
Sí, perfecto. Muchas gracias.
We start the conference with the first keynote lecture of today. Professor Salvador Venganza Andraca, School of Engineering and Science Technology, Monterrey, Mexico, is going to present today on quantum computing from the lab to the market. So, brief bibliography of Professor Salvador. Professor Salvador Venganza is a scientist and consultant devoted to scientific research, technology development, technology transfer, and teaching. Is a principal investigator of the Unconventional Computing Lab and a professor of computer science at Tecnológico Monterrey. His work is focused on understanding all scientific and social aspects of computational, as well as on contributing towards economic developments of modern society, and based on science and technology. He is leading scientist in the field of quantum box, co-founder of the field of quantum image processing, and founder of quantum computing in Mexico. He holds a PhD in physics and an MSc by research in computer vision, both degrees awarded by the University of Oxford. He is also hold an MBA and then BSc in digital electronics and computer science, both degrees awarded by Tecnológico Monterrey. So we invite Professor Salvador to give a lecture. Thank you.
Thank you very much indeed for a very kind presentation. I'm pleased to be with you all. Good morning, maybe good afternoon, depending on who's listening and where, but I'm very pleased to be here. My name is Salvador Venegas Andraca, and this is the title of my talk, Quantum Computing from the Lab to the Market. So these are some contact details of mine. And if you want to download this presentation together with some additional files that I have included there, for example, some reports produced by the and published by the World Economic Forum. One of them, I'm a co-author of it. Then you can download all these files together with this presentation in this URL, or you can also read the QR code that is going to lead you exactly to the same folder, to Google Drive's folder. If you can't take this information now, then don't worry, because the very last slide will have exactly this information, the tiny URL together with the QR code. Okay, well, let me start by thanking Dr. Eduardo Lugo, as well as the all other staff members and organizers of this great conference. I truly appreciate the opportunity of talking and sharing what I know about quantum information and quantum computation, so thanks a lot. I also like to thank, of course, Tecnológico Monterrey, the university I work for all the support that I received over this pretty much 17 years of working on quantum computation since I came back from Oxford to start working as a professor at Tech. Well, that's me. We already talked about myself, so let's skip this part and let's now talk about quantum computation. So quantum computation, first of all, I think that it's a good idea to kind of decompose the name in order to find out what exactly we do in this field, because depending on the background, on the academic and scientific interest that one may have, the answer to the question of what is quantum computation will change. So, for instance, when I was reading for my DPhil, I was privileged enough to meet David Deutsch, who's one of the fathers of quantum computation. And in his talks, he always shared that his interest, or his main interest in quantum computation, was to use it as sort of a test bed to think about different say interpretations of quantum mechanics, in particular that one which is known as the multiverse, because Professor Deutsch's scientific interests are very much along those lines. Now, for a computer scientist like me, who are mainly interested in hardware and on the development of algorithms for solving challenging problems, the best definition I've come up with about what quantum computation is the one that we have here. Quantum computation is a multidisciplinary field focused on the development of computers and algorithms, that is to say, hardware and software, based on the quantum mechanical properties of nature. The very birth or origin of quantum computation comes with the fact that, or comes from the fact, sorry, that the trying to develop algorithms for, well, let me pose it this way: the will of developing efficient algorithms for exact simulation of physical systems, in particular quantum mechanical systems, usually leads us to an impossible scenario, because the number of computations, the number of calculations that we have to run in order to have an exact simulation of a quantum mechanical system usually grows exponentially. Therefore, we end up being in the NP realm, and And therefore, it's usually the case that we have to choose between being efficient or being precise. But the quest of finding efficient algorithms that could exactly simulate the behavior of quantum mechanical systems led to several scientists, among them, and first of all, Richard Feynman, to think of developing a new kind of computer, a computer that instead of being based on the rules or the laws of classical physics, would actually work based on the rules of quantum mechanics. See, so that's, and therefore one of the goals of this field is the development of faster algorithms. We're going to talk about that in a second. Okay, so that's a definition of quantum computation, particularly, say, suitable for computer scientists like me. And, well, quantum physics is a scientific field focused on describing and predicting the behavior of matter and energy at very small scales. For instance, 10 to the minus 10 meters and smaller. That definition is, of course, a big picture. But the idea basically of say what quantum physics is to give you a hint as to what kind of systems we would use for creating quantum computers. There are many technologies for building quantum computers nowadays. We can, in the beginning, there were, for example, NMR-based quantum computers. Now, I would say the most popular hardware platform for the development of these kind of machines is superconducting systems, but we also have quantum optical systems for the development of processors for quantum computers and so on and so forth. So there's a number of technologies now for building quantum computers, but all of them, regardless of the particular properties or the particular materials that we use, follow the rules of quantum mechanics, for describing and predicting their behavior, right? And therefore for describing and predicting the computational power of the algorithms that we may run over those systems. Now, that's quantum physics. And theoretical computer science was born, as a matter of fact, as kind of a mixture of engineering, physics, and mathematics, but eventually, and quite soon, it became a branch of mathematics that focuses on answering this question. What are the fundamental capabilities and limits of computers? So one of the holy grails that we try to find in quantum computation is whether the properties of quantum mechanical systems, that is to say, the physical properties of those systems, would allow us to develop better algorithms, where better could mean faster, could be more precise, could mean a number of things that we are in the process of defining in research laboratories and companies. So now, quantum computation, in addition to being a very solid field of it should be in a very solid scientific field, it's also a traversing field which is now transitioning into an emerging branch of technology and business market. Okay? So there's a number of different fields in which we can find now quantum algorithms and the idea of using quantum algorithms for better performance. Those fields being, for example, artificial intelligence, machine learning, computational geometry, and image processing. We also have an ecosystem that's been known for a number of years now, which is composed of investors like Breakoff Capital, Quantum Valley Investments, global companies, the usual suspects like Microsoft, Google, IBM, Amazon, D-Wave, Quantinuum, and Quantinuum is actually was formerly known as Cambridge Quantum Computing, but there was an alliance with Honeywell, with all the almighty power of such a big company. They created a much larger company now known as Quantinuum. There are also small to large companies that will, of course, play a very important role in the value chain of the quantum computing industry and the quantum computing technology industry at large. These companies, for example, are OneQubit, Rigetti, Quantum South. Quantum South is, as far as I know, the first and so far the only successful company founded in Latin America for the development of quantum algorithms. Of course, we want to have many more successful examples like Quantum South. We were very proud of this company in Latin America. We also have Xanadu, Zapata Computing, StrangeWorks, Cureka, and several others. So the idea of mentioning these companies is to give you a hint, give the big picture of the different players in this ecosystem, which is constantly growing, and therefore looking for new ways to add value to many fields in which we can use quantum computers. And we'll talk about some of those fields shortly. And we also have governments, of course. I mean, any scientific field which is to be nurtured, to be developed, and therefore, and later on, to be transformed into an emerging technology market, needs the support of companies and governments. And here we have many governments, very powerful, that have been sustainably providing resources, not only money, but also human resources and many, providing all the basic elements of the ecosystem that will allow quantum computation and quantum technology in general to develop in their territories, like the European Union, the United Kingdom, the United States of America, China, Japan, Australia, etc., and so on and so forth. These are just some of the big players. Now, let me now focus on some, mathematical and physical parts of the differences and similarities between computer science, what we would call in the field classical computer science, meaning digital or a la Turing computer science, and quantum computing. So the first thing I would like to say is that a bit, as we know, it's the fundamental unit of information processing in what we call, as I said, classical computation. Let me explain this briefly. In quantum computation, we use the term classical computation to really mean digital computation or a la Turing or Turing-based, universal Turing machine-based computation. The reason for using the word classical is a heritage of physics, because in physics, anything which is not quantum is classical. That's just the way we use words in physics. Okay, so, but really what I mean when I say classical computation, I mean Turing-based or universal Turing machine-based computation. Okay, now the fundamental unit of information processing in classical computation is a bit, which can be thought as an element of a scalar space in which we have two different symbols that represent two mutually exclusive outcomes of a very big portfolio of different experimental realizations. We can build bits using relays, using transistors, using switches on and off. There are many ways to do it, but no matter what realization we choose, we know that the way we have to represent the bit is as an element of a scalar space in which we have two different and mutually exclusive outcomes. In quantum computation, we use vectors as the fundamental unit of information processing. And as a matter of fact,
Regina, muito bom, please.
Sorry, do you have a question? Okay, thank you. And as a matter of fact, well, this is the formal definition of what a qubit is. And here you may find some kind of a weird notation. Let me go back to one slide to tell you that the way we write vectors in quantum computation, well, in quantum mechanics and in quantum computation, is by using the direct notation, which consists of using a vertical line together with a kind of a greater than symbol. Okay, and we call this a ket. Now, the reason for using this particular notation is that, say, calculations in quantum mechanics can easily become really cumbersome. And by means of this notation, things can speed up. So that's basically the reason. And the direct notation is basically, everybody uses it in quantum computation. So that's why it's a good idea to introduce this notation. Now, as you should remember, vectors can be written in different ways. So this is kind of a flashback. We can write a vector, visually as an arrow. But we can also write it as an ordered pair, or equivalently as a linear combination of vectors that constitute the basis of the corresponding vector space, together with coefficients, which in the case of R2, which is what we have here, what we study in elementary school, A and B are real numbers. Okay? Now, a qubit, which is, as I said, a quantum bit, is the universal, it's fundamental information processing unit in quantum computation. It's a vector. It's a vector which really resembles what we have here in the sense of being a two-dimensional vector, okay? But it's different from this definition, given that the coefficients that we're going to use to define a qubit will be complex numbers instead of being real numbers. So the formal definition of what a qubit is right here. So a qubit, formally speaking, is a unit vector, meaning a vector which is its length or its volume is equal to 1. It lives in a two-dimensional complex vector space, and can be written, and that's usually the case, we write it down as a linear combination of a given or a chosen vector space basis. Okay. Now, why is it that we use vectors instead of using only scalars in quantum computation? It's a heritage. It's inherited from the mathematical and physical properties of quantum mechanics. Okay, so all quantum mechanical systems are described by means of elements in linear algebra. We use vectors to describe very large quantum systems, and the simplest, I would say, the simplest quantum system that we can use for information processing purposes is a two-dimensional vector. Given that we would like to have kind of a parallel, the counterpart in the quantum world of a bit. If a bit is defined as an element of a scalar space in which we have only two elements, on or off, then we may say that, well, that the closest counterpart of that definition in the quantum world would be a vector living in a two-dimensional space, right? So that's basically the rationale here. What time is it? Okay, you have to hurry up. We can write down a qubit in different ways. So we can use this general representation. We can also use by means of using the Euler's formula and a simplification coming from the physical properties of a qubit. We can also write it down as we have it here as combination of trigonometric and exponentially complex exponential functions. And we can draw it actually using the Bloch sphere. So all these are tools that we use quite frequently to develop quantum algorithms, to develop the mathematical basis of quantum algorithms. Now, we use quantum bits, we use qubits to build algorithms, okay? And, well, as I was saying in the beginning of this talk, that must be a good reason for learning, for a computer scientist, for instance, for learning a new language that consists of using linear algebra to describe a new kind of computation, together with learning quite a bit of quantum physics. That's going to take a while, because it's not easy to. That's the truth. Quantum mechanics is a fascinating subject, but it takes time to learn the basics of it. So why is it that we would be interested in making all this investment, let alone the amount of money that has to be also invested in the development of quantum hardware? And one of the answers is that we would like to have better algorithms, meaning we would like to use quantum mechanical systems for having better solutions to challenging problems in engineering, finance, computer science, and many other fields of human endeavor. Now, better usually translates into faster. We would like to have faster algorithms. But here the word faster has two meanings, actually. The first one is to take advantage of the physical properties of the hardware that we've been given access to. For instance, if we are competent programmers and we have a problem that can be parallelized, and we have hardware that has, say, for example, we're given access to 10 GPUs together with other processing units that have several cores and several pipelines, then being competent would actually translate into being able to develop a program that takes advantage of the parallel properties of the hardware we've been given access to, okay? So that's basically what we've been doing in quantum computation since the very birth of this discipline up to, I would say, 7 or 8 years ago. That is focusing on the physical properties of the hardware that we may have access to, okay, on the mathematical and physical properties of quantum mechanical systems in order to develop quantum algorithms. And this physical process that we have in this slide is an example of it. Let me just go briefly. It doesn't matter whether you fully understand the mathematics of it, because the goal of this process is to show you a truly fascinating property of quantum computation. So here we have a qubit, okay? So this is a qubit which is initialized in a particular value that we're going to call 0, okay? It's not a zero vector, it's just a label that we use to refer to a particular vector we're going to use, okay? So here we have 1 qubit plus n more qubits. So we have in total n plus 1 qubits, okay? And let me make now a parallel with classical computation. If we have a digital circuit, say a circuit that has ANDs, ORs, NOTs, NANDs, XORs, etc., so on and so forth, then in order to design and run an algorithm using gates, we need to have particular combination of the gates that we would like to use, together with some definite values, the initial conditions that we shall provide, to the bits that will be transformed as they go through the circuit. So in here we have, this would be the equivalent of having the initial values of the n+1 qubits that are going to go through a circuit, which in this case is composed of n H gates. We call them Hadamard gates in quantum computation, but the name doesn't matter now. Just H gates. It's a particular kind of quantum gate, together with another gate that we call the identity gate. Okay, so we have n+1 qubits that will go through n+1 gates, quantum gates. The main difference, I mean, for a computer scientist, the main difference between a digital gate and a quantum gate is the mathematics that describe each one of them. So the mathematics that describe quantum gates are those of unitary gates that, if you take a course of quantum computation, you'll get to know what that means. Okay, but this is just, I mean, there are of course differences when building the classical and quantum hardware, but for a computer scientist who's focused on developing algorithms, all that matters, or what matters most, is the mathematical properties of these gates. So we make these n+1 qubits go through n+1 quantum gates, and what we get as a result is a summation that is composed of an exponential number of different elements, which is, you may agree with me, quite remarkable. The fact that we have a polynomial amount of resources, both in the sense of the fundamental units of information processing, meaning qubits, together with the quantum gates that we're going to use in order to transform the information contained in those qubits. And then what we get as a result is a summation in which we have an exponential number of different components. Okay? Now, this is possible, this is indeed possible, because of the vectorial properties of quantum bits, basically because of the fact that we use linear algebra to describe the behavior of a quantum mechanical system. Okay, so learning how to use those mathematical properties for developing algorithms has been the focus of I would say the full quantum computing community for many years now. Now, there's another definition of faster, which is that of hold on. In addition to proper pertinent use of the hardware that we have access to, we also need, or I would say the next step, saying the sophistication of efficient and very good algorithms, is to develop ingenious algorithmic techniques for solving a problem. For instance, if we would like to use a brute force algorithm for solving the traveling salesman's problem, well, we know that we can do it. It's just basically computing all the different paths that could be followed that we could go through in a graph. But the problem with this algorithm, with a brute force algorithm for solving the TSP, is not whether it exists or not. It does exist, and the problem can always be solved by a brute force approach. Trouble is the amount of time that we need to invest, or the amount of resources that we need to invest for that purpose using that algorithm, which is a factorial amount of resources. Now, if instead of using a brute force algorithm, we use the Bellman-Held-Karp algorithm, well, this algorithm is still inefficient, but it's less inefficient, much less inefficient than the brute force algorithm that we have here, because the computational complexity of the Bellman-Held-Karp algorithm is of the order of n squared, and to the second power times 2 to the n. So the point that I want to make is that simple solutions that are that take advantage of the properties of quantum hardware or classical hardware, well, that could be a good idea depending on the nature of the complexity of the problem that we would like to solve. But the next step in quantum computation, as it was the next step in classical computation, was in addition to making proper use of the hardware that we have access to, in addition to that, to develop ingenious algorithms for solving challenging problems. So that point in quantum computation, the development of algorithmic techniques, for example, the quantum equivalent or the quantum cousins of a divide and conquer dynamic programming, and so on and so forth. This is yet to come. Okay, people, I mean, some groups have been working on the development of new quantum algorithmic techniques, but this is a very new field in which many fruits is expected to be truly fruitful over the next years. Okay, so now let me hurry up because I have only 7 minutes to finish. Now, this is a parallel that I would like to use to show say the similarities and differences between classical algorithms or digital algorithms and quantum algorithms. Here we have on the left-hand side of the of both circuits the initial conditions of bits and qubits. We also have a number of different gates, which are either digital or quantum gates. Okay, time flows in both cases from left to right, so to speak. So time flows, I would say, as our intuition says so. And information also flows from left to right. Now, there are some very important differences between quantum algorithms and classical algorithms that I will not dwell into now, but one of them will suffice, which is the fact that reading information, meaning reading the outcome of a digital algorithm, is a trivial task in the sense that there is nothing else to do but just to use a physical system, a measurement device, in order to extract information contained in the physical system in which we're storing bits, okay? And our intuition would say that what we read, I mean, the data that we read, under the assumption that the hypothesis that the measurement device is working properly, as well as the system in which we have storing data, the data that we get as a result of that measurement will be exactly the information or the data, sorry, that was stored in that device, okay? Now, that is to say, we read 5 volts, okay, in a transistor. The measurement device is right. I mean, it has been properly calibrated and so on and so forth. Then we may say, well, this is exactly the value that we had there, and therefore that's equivalent to 1 bit. Now, in the case of quantum computation, reading information is a probabilistic process, okay? And that leads to very, honestly, very exciting, fascinating properties of quantum algorithms that you can, of course, get into, learn if you take a course on quantum computation. Now, there are other ways to write quantum algorithms, like using differential equations. This is the mathematical basis of say, for example, D-wave quantum computers. There are D-wave quantum computers are quantum annealers. These machines have been developed with the goal of solving optimization problems, and the mathematics that describe the basic behavior, fundamental behavior of those systems is shooting this equation with particular values for this operator that is known as the Hamiltonian of the system. So the point I want to make is that in addition to having a similar, say, rationale for developing quantum algorithms, which is that of quantum gate-based quantum computation, we also have other paradigms that would require computer scientists to learn, new mathematics, or to learn mathematics, to have a deeper understanding of mathematics that may not necessarily be part of the syllabus of a computer science or a computer scientist or a computer engineer. Okay, so that's quantum annealing and quantum adiabatic computation for you. And there's this is one of the latest trends in the development of quantum algorithms, which is known as variational quantum algorithms. This is basically a control system. This is a feedback control system in which the plant is a quantum system and the feedback is provided by a digital algorithm, usually a machine learning algorithm. The idea here is to run a quantum algorithm on a computer, on the actual hardware that we have, on the actual quantum hardware we have, which is hardware that it doesn't have error correction techniques yet. It's got some fluctuations on the actual robustness of the computation, of the physical processes of computation in those machines. The machines that we have now, the quantum computers that we have now are, in my opinion, and in the opinion of many other colleagues, equivalent to the machines, to the mainframes that were developed and put in production back in the 60s of the last century. Meaning, we now have quantum computers, but there is still a gap that is to be filled in terms of the robustness and scalability and modularity of those machines. Now, the good news, listen to this, the good news is that we now have quantum computers, and we have had quantum computers for a number of years now. When I began working in this field in 2002, people thought it was simply pretty much it would take 100 years or any number of years that we may think of to develop a quantum computer. But we now have it. So the development of quantum variational algorithms is a way to make proper use of the hardware that we have now in order to keep on working on the development of better computers. Now, I got the chat here that I suppose is to say that I have to finish. Is that so, Dr. Lugo?
Sí, nos quedan 5 minutos, doctor.
Okay, muchas gracias. Thank you very much. I'll finish now. So there's a lot of information here that you may be interested in taking a look. If you have questions, please feel free to send me an email. There are many applications of quantum computation, like the quantum teleportation protocol, which is, I mean, this protocol has been experimentally realized in many countries. So it's a fact. We teletransport, however, information. We don't teletransport mass. That's out of the question. Okay, what we use what is teletransported or teleported in this protocol is information containing a qubit, and this is the basis of the development of the next generation, the next step in internet, which is the quantum internet. This is the best book that I know about this field, so I strongly recommend it. There are several algorithms that have been developed over the last 25 years, 30 years to take advantage of quantum computation, of quantum computers. But now let me jump to QKD is a way to produce private keys for cryptographic purposes that we could, I mean, these keys could be used later on in DES or AES cryptographic protocols. Al Aspect is one of the Nobel Prize winners this year in physics. And the simulation of quantum physical systems using quantum computers, as I said in the beginning of this talk, is a very important and hot topic. Okay. And now let me jump to the very end so that you have questions. We have time for a few questions. As I said, quantum computation is now, or quantum technology in general, is an ecosystem in which there are many players, a lot of money, and the possibility of developing a new paradigm in many fields of technology and human endeavor, which is very promising and exciting. There are global companies, some companies that are going from small to large. This is the number of patents that have been filed over this from 1983 to 2020. 1,000, just a bit more than 1,100 patents filed in 2020 gives you a very good idea of how exciting and open to new developments this field is. Okay. Finally, these are 3 reports published by the World Economic Forum. I strongly recommend you to take a look at them because these documents provide a very interesting link between research, industry, and economic development. I was privileged enough to be a co-author of this 3rd document entitled Transitioning to a Quantum Secure Economy. These are some of the things that we do in my lab, who we are here. We work on quantum walks, quantum image processing, the analysis of biological data using quantum algorithms. This is a Facebook wall that I founded a number of years ago, in which we talk about quantum information science and technology in Latin America. We talk about science, technology, business, economy, etc., so on and so forth. So feel free to join if you feel like. This is a course that I have in my YouTube channel. This is of course free. It's 40 hours of training. It's an introductory course to quantum computation in Spanish. So feel free to take a look at it. Quantum Latino is a very important event, which in 2023 is going to be its 3rd edition. In 2020 and 2021, we worked very hard on presenting the several developments, research groups, and leading scientists in quantum computation from Latin America or working in Latin America in the many different branches of quantum technology. The next year is going to be held in June, as it was in the previous cases, June 2023. The World Quantum Day and conclusions. This is the most important conclusion. This is my very last slide. There are many conclusions that could be held, but this is the one I like the most. This is the first computer that I had access to and wrote a program. I coded in it. It was Timex Sinclair 1000. CPU was a Zilog Z80 with 2 kilobytes of RAM, and I had to plug it in my TV, black and white TV. And a few years later, meaning about 35 years later, I had access to quantum computation and to the first quantum processing units that were developed. And so the reason for saying that this is a conclusion is the following. I've been privileged enough in my lifespan to have access to two technologies that are crucial for the development of mankind, for the economic and the development of mankind, for the robustness of the social fabric of our species. And this is exactly what's going to happen to younger people. But not that young anymore, but to young people, they will have access to many technologies. And being a professor, what I can say here is that we professors and the full society in general has to support not only the development of new technologies for the benefit of our society, but also the training, the unconditional support of the training and education of our young, so that they can become, masters in this and many other technologies to come. That's it. Thank you very much indeed for your time. And these are the contact details I mentioned in the beginning of my talk. And feel free to ask any question you may have. Thanks a lot.
Tenemos tiempo para una pregunta. No sé si hay alguien interesado en preguntar.
Si la quieren decir en español o en inglés es lo mismo, ¿ok? Con todo gusto.
¿Quieren preguntar en español o inglés? We have time for one question. Es que tengo ponerlo para escucharlo, pero... ¿Sí? ¿No? ¿Nadie? No hay línea, no hay preguntas. A ver.
Hola Salvador, soy Eduardo.
Hola Eduardo.
Bueno, una pregunta. Estamos en una facultad de física aquí en Puebla. ¿Y cuál sería el mapa de esta tecnología? ¿En cuánto tiempo crees que empecemos a ver productos ya en el mercado? Esa es la primera. Y la segunda, que tiene que ver con la primera, es ¿cuál sería tu sugerencia para un estudiante de física para seguir en un campo como este de la computación cuántica?
Gracias por las preguntas. Pues la primera, yo respondería lo siguiente. Productos, el cómputo cuántico, el cómputo cuántico es una disciplina que al menos en el futuro cercano, estos en los siguientes 5 o 10 años, va a estar concentrada en nichos específicos que tienen que ver con problemas abiertos en ciencia, ingeniería, finanzas, computer science como machine learning. Igual y dentro de 20 años, uno nunca sabe, ¿no? Pero igual y dentro de 20 años hay un Excel cuántico, ¿no? Pero ahora yo no lo veo. Y no lo veo por una razón, porque las computadoras cuánticas y las computadoras digitales van a vivir en coexistencia haciendo cada una lo mejor que sabe hacer. Entonces, para bases de datos muy grandes, sean relacionales o no, para cálculos estilo Excel, para comunicaciones en muchos sentidos, para muchas de las actividades que hoy llevamos a cabo utilizando computadoras y sistemas digitales, realmente no hay necesidad de brincar al mundo cuántico, al menos en el futuro cercano. Uno nunca sabe, ¿no? A lo mejor pasa dentro de 20 años, pero lo que sí puedo visualizar claramente en la siguiente década y la siguiente 1 y 2 décadas, es el hecho de que vamos a tener computadoras cuánticas interactuando con computadoras digitales, haciendo cada una lo mejor, ¿no?, de su repertorio. Y el caso de las computadoras cuánticas, estas máquinas son muy buenas para varias cosas, entre ellas para resolver problemas de optimización. Entonces, el foco o uno de los focos en el uso de computadoras cuánticas en los siguientes años es la solución de problemas que se pueden traducir a problemas de optimización en matemáticas y en ciencia computacional. Ejemplos de ello son el desarrollo de nuevas moléculas, que es uno de nuevas moléculas particularmente para la creación de nuevos fármacos. Solo para dar una idea, el tiempo que le toma una compañía global, ¿no?, una compañía como AstraZeneca, desarrollar un nuevo fármaco se mide en años, y se mide en años no solamente por los requerimientos de carácter pues legal que hay que cumplir, por supuesto, sino desde el inicio en la cantidad de trabajo computacional que hay que hacer para encontrar nuevas moléculas. Y platicando con el director general del Centro de Desarrollo Tecnológico de AstraZeneca en Guadalajara, precisamente en Quantum Latino de este año, nos compartía, a nosotros nos toma un año, 24/7, simular en supercomputadoras las diferentes combinaciones que pensamos antes en papel, ¿no? A efecto de encontrar una molécula que sea susceptible de ser empleada para la creación de un nuevo fármaco. Entonces, la capacidad de producción de nuevos fármacos no solo está limitada por características legales, monetarias, sino también es el mismo tiempo que tenemos que invertir en la simulación de esos sistemas físico-químicos. Entonces, la computación cuántica promete dar resultados en esa línea y en varias otras, en finanzas, machine learning. ¿Cuándo vamos a ver productos en el sentido de algo que se puede vender? Ya lo podemos ver hoy. ¿Ok? Ahora, necesitamos tener todavía unos cuantos años más de trabajo en la parte de robustecimiento del hardware cuántico. Esto es de la inclusión al menos de algunas técnicas básicas de corrección de errores o bien el desarrollo de hardware que no requiera de este tipo de técnicas. Hay varias propuestas al respecto. Pero grosso modo así, abuelo de pájaro, bueno, no abuelo de pájaro, sino grosso modo, ¿no? El big picture de esto es que y con base también en los roadmaps publicados por IBM y otras organizaciones, esperamos que en los siguientes 10, 12 años se construyan versiones de computadoras cuánticas suficientemente grandes como para representar, por una parte, máquinas que potencialmente pueden correr el algoritmo de Shor y en consecuencia producir escenarios de vulnerabilidad en sistemas de seguridad, sistemas de criptografía de llave abierta. Eso lo van a ver bastante detalle en los reportes que les recomendé del Foro Económico Mundial que pueden bajar de esta liga. Es por una parte, ¿no? Y por la otra, el desarrollo de tecnología cuántica para proteger sistemas de ciberseguridad, perdón, también es un área en la que estamos trabajando actualmente, en la que se irán saliendo productos. Ya hay algunos, pues, en el mercado, solo que, pues, no, o sea, no se anuncian, digamos, con la facilidad de Office, porque son desarrollos de nicho, ¿no? Son desarrollos cuya naturaleza, de hecho, solamente la entiende un especialista. Y en la misma lógica está el desarrollo de nuevas moléculas, de algoritmos para análisis de portafolios de inversiones y varias otras áreas. Esa es la primera pregunta, la respuesta a la primera pregunta. Y la segunda era sobre qué camino podían seguir los estudiantes de física, ¿no? Pues miren, un estudiante de física, si le gusta la idea de trabajar en computación cuántica o en comunicaciones cuánticas, tecnología cuántica en general, una es lo que todo físico sabe que tiene que hacer, ¿no? Aprender muchas matemáticas. Y lo mismo le digo a un ingeniero en computación o un computer scientist. El vínculo entre estas disciplinas es la matemática dura y pura, ¿ok? O sea, el análisis matemático, las ecuaciones diferenciales. Hay unas máquinas, hay unas computadoras cuánticas que trabajan sobre modelos topológicos. O sea, esa es una, ¿no? Indispensable. Y la otra es darse la oportunidad de que cada quien desde su disciplina aprenda de la otra. Por ejemplo, los físicos, valdría mucho la pena que supieran al menos las bases de la ciencia computacional. Eso no significa que aprendan a programar, ya saben programar, ya aprenden a programar en las facultades. Estoy hablando de la parte matemática, del análisis de la complejidad computacional y de la computabilidad, de la teoría de la computabilidad en computer science. Eso es bien importante entenderlo para comprender las bases del cómputo cuántico. Y lo mismo para sistemas de comunicaciones, aprender, por ejemplo, las bases de la teoría de información de Shannon y su contraparte cuántica. Y lo mismo para un ingeniero. Un ingeniero tiene que aprender física. No tiene que aprender toda la física, todo lo que sabe sobre física cuántica, pero sí tiene que aprender las bases de la mecánica cuántica para comprender los elementos fundamentales de un algoritmo cuántico. Hay un excelente libro, un paper al respecto, y después se convirtió en un libro que se llama From Civets to Qubits. Lo escribió un físico estadounidense, desafortunadamente ya fallecido, David Mermin. Y este paper, que lo pueden encontrar en el arXiv, arxiv.org, habla sobre la experiencia que tuvo David Mermin enseñando computación cuántica a computólogos. Y les digo que después se convirtió en un libro que publicó, si no me acuerdo, Cambridge University Press. Pero el punto es que él es aprender de la multidisciplinariedad, ¿no? Aprender a vivir cómodamente en ella. Y de ahí, pues cada quien, si a los físicos, un físico en particular que le gusta la parte experimental, quiere trabajar en eso en computación cuántica o en tecnología cuántica en general, a ese tipo de físicos yo lo que le recomiendo es que se vaya al extranjero y se vaya a trabajar a otro país. ¿Por qué? Porque en México difícilmente vamos a desarrollar hardware cuántico. Yo sé que lo que estoy diciendo es bien duro, es políticamente incorrecto, pero yo me distingo por ser políticamente incorrecto. Yo no veo en México una sola organización dispuesta a invertir lo que se tiene que invertir en términos de tiempo, capital humano, etcétera, ¿no? Para construir una computadora cuántica en México. Sí hay trabajos muy interesantes, eso permiten subrayarlo, que están la gran mayoría de ellos contenidos en un trabajo que escribimos durante el año pasado y que está a punto de publicarse a través de la División de Información Cuántica de la Sociedad Mexicana de Física. Es un documento que se llama Apuestas de la Tecnología Cuántica en México. Por ejemplo, en la Universidad Autónoma de San Luis Potosí, mi colega Eduardo Gómez lidera un grupo de investigación experimental que trabaja en el desarrollo de sensores cuánticos para medición de campos gravitatorios. El trabajo de Eduardo y sus colegas es una cosa fascinante, de súper primer mundo, de clase mundial. ¿Okay? Y en ese documento, así como el trabajo de Eduardo, hay otros desarrollos experimentales que se hacen en México. Pero ninguno de ellos se refiere a la creación de una computadora cuántica universal o una computadora cuántica como un quantum annealer, ¿ven? O al desarrollo de sistemas, por ejemplo, de componentes de quantum internet. La única noticia que yo tengo al respecto es lo que hacen en Simvestab Querétaro, que es un laboratorio de tecnologías cuánticas donde trabajan experimentalmente en la implantación de protocolos de QKD. Entonces, el camino, digamos, de crecimiento para un estudiante de física experimental, en mi opinión, ¿no? Que se quiere dedicar a la parte de tecnología cuántica, es o unirse a uno de estos muy pocos grupos que hay en México con trabajos muy específicos o trabajar para una compañía global. En la parte de desarrollo de algoritmos cuánticos, ahí es otra cosa. Ahí hay mucho campo a desarrollar, se puede hacer en México, en Estados Unidos, en varias partes del mundo, pero en particular en México, con el advenimiento de la tecnología cuántica, ¿no? Pues con todo lo que el boom de esta disciplina, hay oportunidad de trabajar en el desarrollo de algoritmos cuánticos para distintos propósitos, ¿no? Análisis de información biológica, portafolios de inversiones, etcétera. ¿Okay? Ya es cuanto, esa sería mi respuesta. Poco larga, pero espero que les haya servido.
Sí, muchas gracias, doctor, por su participación.
Muchas gracias a ustedes. Corto ya la, permítanme, ¿eh? Cierro la. Ok, bueno, pues muchísimas gracias. Les salgo, ¿verdad? Para que puedan tener el siguiente ponente.
Sí, tenemos una pregunta en línea, pero le hacemos llegar sus datos para que lo conteste.
Claro que sí.
Mosby.
Muchísimas gracias. Thank you very much all. Good to talk to you. Have a good day.
Good day. Sí. La conectamos. ¿Me ayudas a conectarla? Yes, please.
Next, we have the workshop section. Professor Andreas M. Costa is going to give on simple magnetic superatoms.
No. El workshop.
Professor Andres is going to give one workshop section on the quantum magnetic correlations.
Do you have pointer? ¿Le podemos acercar una mesa o algo? A ver, subimos la mesa esa.
Okay, I think that's. Do we start now? Or?
Yes, you can proceed.
Okay. Good. Okay, also, what I want to do with you is to show you the way how to do quantum chemical calculation. And to this end, I will use here the program Demon2K. And this is a kind of interactive workshop, which means that you can, of course, ask and put questions here whenever you want, also in Spanish. Yo hablo español más o menos, so por esta razón no tengo problemas con preguntas en español. So I would like to start a little bit with the outline of what I plan to do in this workshop. I'm not sure that we will go through all of that, but we are starting with an introduction into quantum chemistry. And we then go over a set of points that are characteristic for such quantum chemical calculation, such as energy calculations of a molecule, the structure optimization of molecules, molecular property calculations, reactions, and molecular dynamics calculations. And as you can imagine, such a program that does such quantum mechanical calculation is rather large. So for example, D12K, to give you an idea, has something like 2,500 subroutines. And of course, such a program is not developed by one person, but it is developed by a full community. So D12K is developed by roughly 25 to 30 research groups. Each group, let's say, have 5 to 10 people. So then at the end of the day, some 200 people had their fingers in the program. And to this end, you need to coordinate this somehow, such kind of program development effort. And that is done in the Demon2K community. And here's a URL where you can look at the software. At this point, you also can actually download Demon, and you can run, if you are able to run on a Linux partition of your computer or wherever you want, you can run the software directly downloaded from this website. This is not ultimately optimized, but it is good for the calculations, for example, which I show you here. The other point is where we are, so theoretical chemistry at Silvester. That is a bird view of the campus of Silvester Zacatenco. Here is Instituto Politécnico Nacional, IPN. Here is IPN itself, the campus. And theoretical chemistry is located in this building here, where we do have a setup of the following form, that we have our own mainframe. So this is the entry of theoretical chemistry. What you see here, you see here a condenser and a big compressor. So this is a quite big air conditioning. And this air conditioning takes care to our infrastructure, which are two main clusters together of around 1,500 cores. And these clusters are used for the development of the program. So these 1,500 cores at the first moment looks big if you think about one group. But as I told you, there are many groups developing on the code. And so we have continuously, at least on the developer cluster, something like 20 users who are working simultaneously on this cluster. So it's not so that you can do there a large amount of real calculations, because most of the time is used for program debugging and validation calculations. So if we do calculations to a larger extent, we are relying on external computational resources. These are usually high performance computational resources that provide you as a user with several hundred of cores per user. That is, of course, not what we can do with our local infrastructure. So this is my research group here. Is a photo that was done before the pandemic. We are now a little bit compressed. In the moment, we are only 7 people, but we hope to bring it back to the old strengths soon. And yeah, here is the question, what makes us different? So what really makes a difference between, for example, D12K on one side, the program we are developing, or programs that you might know from your educational background or from literature search. So if you compare D12K with Gaussian, or you compare this games or QChem or Orca, or there are many quantum chemical programs on the market. So what makes D12K books? What makes D12K different? Well, the difference is really in the application range. What D12K has is a special implementation form of density functional theory. We will come to this in a moment. And it is called auxiliary density functional theory. And what is particularly on auxiliary density functional theory is that we can work with reduced quantities. So where, for example, density functional theory works with a matrix, we can work with a vector. So that reduces our demand of memory, and this improves and facilitates the parallelization of the program. So D12K is completely parallelized. It's a Fortran 90 plus program that is completely parallelized over MPI. So why do we use Fortran, which seems to be an antique language compared, for example, to C++? Well, we use Fortran because it is an industrial standard. So you have a very clear definition of the context of the language. And you can by using such an industrial standard, you can write programs that run on cellulars. So D12K, for example, runs for some of my student cellulars and the HPC resources. And it is the same source. And the other point is that we do parallelize over MPI, which is considerably more complicated as doing OpenMP parallelization, but we use MPI for the same reason as we use Fortran. MPI is an industrial standard. Again, you can take MPI sources from wherever it comes, and the program will run with it. So this is the reason why we use this combination. So by using ADFT with such a programming, structured programming combination, what we can do is we can extend first principle calculations that are characteristic for small molecules and for maybe femtosecond time evolution in molecular dynamics, and we can go to much larger systems. So we can, for example, calculate system sizes of a few hundred atoms to a few thousand atoms quantum mechanically. So we can calculate small proteins with D12K, and we can do molecular dynamic simulation that reach until nanoseconds. All of that is quantum mechanical. So this is a characteristic for D12K, which makes it different to other quantum chemistry programs. Another development that has been done over the last 10 years or so is that we are combining now in the same code molecular mechanics with quantum mechanics. So with molecular mechanics, we can reach system sizes of, let's say, 100,000 atoms rather easily. But with molecular mechanics, you don't have electrons. So you cannot break a bond and you cannot form a bond. So in the moment you want to simulate, for example, a chemical reaction in a protein, you're lost with molecular mechanics. On the other side, also with quantum mechanical approaches, you might be lost because the protein usually is not 1,000 atoms or 2,000 atoms, but the protein may have 10,000 or 20,000 atoms. So then you cannot use one nor the other methodology. So one possibility to overcome this is to combine these two methodologies and to use in the region where you have the chemical reaction a quantum chemical methodology, and the surrounding region that basically is for you an environment, you use molecular mechanics. And this has been done, I would say, since almost 20 years in the way of combining quantum chemical software on one side with molecular mechanics software on the other side. Also, for example, DMON is combined with GROMAX, or it is combined also with other MM software in the original days. But the problem is, if you combine two programs with each other, you do have data transfer, which slows down your calculation. So what we have done over the last 10 years or so is we have incorporated molecular mechanics and quantum mechanics in the same code. So you do not have data transfer outside the program. In this way, you have an extremely fast, pure MM, this is how this is called, methodology. Okay, let me show you some examples here for why do we use quantum chemistry. And I must admit that my example is now not an example that comes out of health science or so. It is an example from cluster science in which I'm working mainly. And what I'm showing you here are collision-induced dissociations of copper clusters. And what you can obtain from these experiments is basically the binding energy of such neutral copper clusters. And what you see here are two different CID experiments done with the anionic and with the cationic copper clusters, and they are then corrected to obtain the collision-induced dissociation of neutral copper clusters. So if the experiments would run perfectly and everything would go well, then you would expect that these data points, which you see here, are overlapping each other. They should be at the same, they should give the same binding energies for the neutral copper clusters. But what you see here is that this indeed is not the case. The data points are quite different. And now, of course, the question arises, which of these data points are the right ones? And in this sense, you can do calculations which are based on quantum mechanics. And you can see here that the anionic collision-induced dissociation experiment gives data points that are much closer to the calculated ones than you see here from the cationic. And you can then go back with this information to the experimentalists, and you can tell them, look, from our calculations, it looks so that this experiment is more realistic than the other. And then the experimentalists, they look back into their experimental setup, and in fact, the people found that this here was not a problem of the particular experiment, but it was a problem because they started with cationic clusters. They had to correct for the charge in order to get the binding energies for the neutron. And these corrections, there goes in electron affinities and ionization potentials, and these data, unfortunately, were not good enough to obtain the correct trend. So in this way, you see the combination between computational chemistry on one side and experimental chemistry on the other side. And of course, if you can go now to larger systems, then you can also do this in molecular biology. That is one of the steps that you will go with QMM. Now, once you obtain these calculations, as you can see here, you do not only have the energies of the binding in this cluster, but you also do have the structures. And if you look at the cluster structures, then something is quite intriguing. If you go until the copper 4, you see that this cluster is planar. And that is completely, when this was published some 20 years ago, this was completely against basic textbook knowledge. Because if you think about a metal, well, that should be a close packing. This is a metallic bond. So, but if you have 4 copper atoms, then the structure of these 4 copper atoms is not a tetrahedron, which is an emulation, so to speak, of the close packing, but it is a planar rhombus. And if you go to 5 and 6 atoms, you also see these structures remain planar. And that is, of course, something which was so unexpected that nobody did an experiment on that. Nobody experimentally thought that these clusters were planar. They were always thinking, okay, these are something like, I mean, drop-like models of metals. But no, they're not. They are indeed planar structures. And this comes out from calculation. So once these calculations were done, if you go now to larger clusters, in fact, these clusters then become 3-dimensional. Once these calculations were done, experimentalists said, okay, also we don't believe the calculations, right? That's nature. We don't believe experiments. Experimentalists don't believe calculations. We want to look if this is really true, if these clusters are really planar. And they developed very, I mean, sophisticated experiments based on diffusion of these clusters in a gas, in a carrier gas. Usually this is argon or nitrogen. And indeed they found this is true. These clusters are planar. And if you go, for example, to gold clusters, this planarity even continues here until, I think, 12 atoms or something like this. And this is experimentally verified after the theoretical discovery of the planarity of these clusters. So this is a motivation. Why do we do quantum chemistry, right? So one point, of course, is to elucidate structures of molecules, and in the best way to elucidate structures of molecules and of systems before they are even synthesized. That's the idea. And to do this in a predictive way. So now we do some, these are slides which are quite dense, but we have seen already kind of symbolic in the previous talk where we were talking about quantum computing. A word to quantum computing here at this point, maybe. So where's quantum computing for quantum mechanics for molecules? Well, quantum computing for quantum mechanics and molecules is at 2 orbitals, with which you can do the H2 molecule. So quantum computing for molecules is in the moment at the stage where quantum chemistry was some 100 years ago. That doesn't mean that it needs another 100 years, but it clearly means there's still a long way to go before, and this is of course one of the dreams, you could put a quantum system like a molecule onto a quantum computer and then obtain the information like the structure or like the energy of the system. There are also some issues here which are quite important to realize if you want to connect from the very fundamental, from the basic theory, down to such applications that you really calculate molecules, that you calculate molecular structures. Our starting point is always the molecular Schrödinger equation. And if you look at these equations, the first thing that you see is we have a Schrödinger equation that is time independent, because we are looking and we are searching stationary states. A somehow crazy situation, and this comes out of quantum mechanics, is even so this Schrödinger equation is time independent, the energy, which is expressed in the Schrödinger equation by the Hamilton operator, contains these terms, these 2 terms here in front, which are kinetic energy. So you have a time-independent equation that contains kinetic energy. What does it mean? Well, who are here the physicists? Who is physicist? Physicists. Okay, they are physicists. Okay. Who is mathematician? Mathematicians are in the moment free, so if you would have raised your hand for mathematician, I would have not looked at you. Is there a chemist in the audience? Chemist? Ah, okay, chemist, that's good. Okay, but this is a question to the physicists. How can it be that we have a time-independent equation and we have kinetic energy inside? What does it mean? What does kinetic energy mean in quantum mechanics? Yeah. ¿De qué? No, esto no es correcto. Si tú buscas en un molecule, ¿no? Tú tienes un molecule y tienes una función de onda y calcula la energía cinética en puntos, en diferentes puntos, es diferente. So, no es constante.
El tiempo es constante, el espacio varía.
Exactamente. ¿Y cómo es la variación en el espacio? Esto es muy interesante. The kinetic energy in quantum mechanics describes the curvature of the wave function. And now comes something which is very important. The curvature of the wave function can be positive or negative, which means you can have positive or negative kinetic energy in quantum mechanics, not in classical mechanics. So do not write your exam with some negative kinetic energy in classical mechanics and say Andreas has told this. No, this is not what Andreas has told, okay? Andreas has told kinetic energy can be negative in quantum mechanics, not in classical mechanics, okay? So because it measures the curvature. And the other point is when you look at these terms here, this is easy for the physicists, but I think also for the chemists, you see the only thing what we have is electrostatic. So our problem to solve is actually and quantum mechanical part, which is characteristic for quantum mechanics, namely for the quantum mechanical kinetic energy, plus a static electronic part, which is electrostatic. So there's no electrodynamics inside a molecular system if we are searching stationary solutions of the Schrödinger equation. There's no electrodynamics. And that has resolved the paradox you have in the Bohr model. If you remember, the paradox of the Bohr model was if the electron is circulating the nucleus, then it will introduce radiation. This radiation will take energy out of the system and the electron will end up in the nucleus. Yeah. You solve this problem in quantum mechanics by a new form of kinetic energy that is characteristic to quantum mechanics, and you have no time dependency in the electrostatic. Okay, questions at this point? Everybody happy? Great. So then, if we look at this Schrödinger equation, you see the Hamilton operator is a completely abstruse mathematical concept, mathematical construct, which we have here. And the other thing is the wave function. Also, the wave function is nothing you can measure. So every 10 years, there is a Nature or Science paper that somebody claims has measured a wave function property, not the wave function itself, but a wave function property in some indirect form. And then there are 1 or 2 years of discussion, and until now, the result was always, no, sorry, but the wave function is not a measurable quantity. Until now, it is a not measurable quantity. At this point, the wave function, and this is here denoted by the small r and the capital R, depends on the coordinates of the electrons. This has the coordinates of small r, and on the coordinates of the nuclei. This has a capital R. So this is an ensalada of particles. Our elementary particles here are electrons on one side and nuclei on the other side. We do not go below nuclei. So protons, neutrons, or even quarks, we all group together and we call this thing a nucleus. Okay, but our elementary particles are electrons and nuclei, and they are joined together here. And if you now think, I'm happy to have a chemist here, one of the fundamental concepts of chemistry is molecular structure. Right? A chemist looks at, oh yeah, structure, it's like an architect, right? Oh, this is a planar molecule, benzene, this is a planar molecule. And cyclohexane, no, cyclohexane is three-dimensional, you have the kind of structure. This structure of molecules is not in this equation, it's not there. Because the wave function is an ensalada of our elementary particles, which are electrons and nuclei. So how do we incorporate, how do we obtain molecular structure out of these fundamental physical equations? Well, we do an approximation. And that is the so-called Born-Oppenheimer approximation. The Born-Oppenheimer approximation, the idea behind the Born-Oppenheimer approximation is that we separate the electrons from the nuclei. So we separate the small r from the capital R. And you can do this mathematically, and you can do this very nicely. And there are many, many issues with this, but we don't discuss this. Bottom line is, if you do the Born-Oppenheimer equation, approximation, and if you do this separation of electrons and nuclear coordinates, you obtain two Schrödinger equations. You obtain one Schrödinger equation, which we call the electronic Schrödinger equation. And this electronic Schrödinger equation solves for the electronic wave function. You see, this C only depends on small r. This is a different C as this one. This is the electronic wave function. And the other Schrödinger equation, which we will not discuss further on here, is the nuclear Schrödinger equation. For us, interesting is this electronic Schrödinger equation. This is why there's no red box on this. And this electronic Schrödinger equation, yeah, this is all the effort which we are solving in quantum chemistry. So all our effort, as not for all people, but at least for me, all my effort goes into the solution of this electronic Schrödinger equation. So why is this electronic Schrödinger equation for us so interesting? Well, again, this electronic Hamilton operator, which is the same as this, only the nuclear kinetic energy is gone away, does not have physical meaning, neither has the electronic wave function, but this energy here, as the energy of the original Schrödinger equation, this energy here is what we call a physical observation. This is a measurable quantity. That is something you can find experimentally. And as you can see, this electronic energy is a function of the capital R. And the capital R are the nuclear coordinates. And now comes the most important concept in this course, and this is the concept of the potential energy surface. The potential energy surface, what this is nothing else as a function of these electronic energy. So this electronic energy is the axis here. And then we have here two axes, which can be some kind of nuclear coordinates. So if you think, for example, of water, you can have a bending, and you can have a stretching. Let's assume the stretching is for both hydrogens the same, then you have two dimensions. So that would be a water movement in C2V, and this point would C2V. So this would give a potential energy surface of this form by solving these electronic Schrödinger equations. And on these potential energy surfaces, you can find here different types of minima. And these minima on the potential energy surface are stable chemical structures. So each of these minima is what we call in chemistry an isomorphic system. Yeah. And so, for example, if you have keto-enol tautomery, that is for the chemist in the audience, then one here you have the keto and here you have the enol. Yeah. So if you do have some kind of different minima with respect to rotation, cis trans also there you have these different minima. And now you can even have a chemical reaction. You can go from one minimum to the other. And when you go from this minimum to this other minimum, you can go over the so-called minimum energy path. This is this red path, which is here on this slide. And this is what you find in many of the chemical textbooks. Yeah, so when you, oops, I haven't counted with a microphone, so I'm not a third hand actually, but I will do this so. So if you think about pictures of this form, where you do have here somewhere the energy, and here you have somewhere the reaction coordinate, you have a picture of this form, what you see here, then these points are minima. So these are exactly the points which you find here on the surface. Now, what is very often, as a very simple question we have in the introduction, also when people enter in the chemistry department, the question is, what is this for a point? We call this a transition state. And then the question is this a maximum? And when you look at this curve, then you say, oh, this looks like a maximum. But if you look at here, then you see this is not a maximum. So the transition state is only a maximum in one principal direction and a minimum in all other directions. So we call this a first order settle point. Yeah. And with this information, you basically have all the information about chemistry, if you make it correctly, because you have the thermodynamic of a reaction. This is the difference in the energy of the minima, and you have the activation energy, which is the difference of the energy from the minimum where you start to the transition state. So you have the thermodynamic information and you have the kinetic information of the reaction encoded into these potential energy surface. And now you might understand why some people really dedicate their life to solve this electronic Schrödinger equation, because it is really fundamental for predictive chemistry in such a kind of computational approach, in such kind of simulation. There's a problem, however, as usual in life. These potential energy surface, if you solve these electronic Schrödinger equation, you don't get the full potential energy surface. What you get is, you get one point on the surface. And when you want another point, you have to solve a new electronic Schrödinger equation with a changed nuclear configuration. So you have not to solve this equation one time, but you have to solve this equation many, many, many times. And you have very interesting mathematical problems here, if you think about that. So think about you're at this point here, and you solve this electronic Schrödinger equation, then you're at this point. The only information is this point here on the potential energy surface. And then the question is, where is the next minimum? Where do I have to go to this minimum? So you have to make a minimization without knowing the function that you minimize. Yeah. This is quite sophisticated mathematics, but it is a well-known and well-solved problem, at least as long as you are going into one minimum. A much more difficult problem is when you say, okay, I can go from here in one minimum, if I at another point I go in another minimum, okay, how many minima do I have on this potential energy surface? And the usual situation is a lot. As larger your system, as more minima you have on the potential energy surface. And this gives rise to the problem of so-called global optimization, which is basically the question, which is the lowest local minimum for a given system, for example, for a protein. And if you have a couple of thousands or hundreds of thousands of minima on your potential energy surface, then you can imagine that this search for the global minimum is extremely demanding. And this is where today, for example, machine learning algorithms are introduced in finding such global minimum. Yeah? And we can discuss about how good are these machine learning algorithms with respect to more traditional algorithms, as surface hopping, or let's say parallel tempering molecular dynamics. So there are simulated annealings. So there are different types of algorithms how to solve this problem of global optimization. And I would not say that today we have, so to speak, the bulletproof methodology how to do this. Yeah, last but not least, we usually do not solve the nuclear Schrödinger equation. Once we have solved the electronic Schrödinger equation, we use a classical propagation of the nuclei. This is called molecular dynamics, and in this particular form, Born-Oppenheimer molecular dynamics. And you see here that in this propagation, in the potential for the nuclei goes the solution of the electronic Schrödinger equation. Yeah, so also there, you need to solve the electronic Schrödinger equation. If you do Born-Oppenheimer molecular dynamics, that means solve the electronic Schrödinger equation and then solve a classical equation of motion for the nuclei, obtain a new structure, and resolve the electronic Schrödinger equation. And this you do again and again and again and again. And this is why BOMD, as Born-Oppenheimer molecular dynamics, is so much more expansive as if you do molecular dynamics with a force field. Because in the force field, you're only solving this, and this kind of potential comes from a parametrization. Yeah. Questions here? That is disappointing. Are you fine with the English? Please.
Bueno, una parte, entonces la parte experimental se podría tomar ahí, ¿no? Para tener todos los parámetros.
Ya, also, sí, exacto, ¿no? Also, para un campo de esfuerzo es posible obtener esto como parámetros, ¿no? Como parámetros experimentales, ¿no? Por ejemplo, de una análisis de frecuencia, ¿no? De infrarrojo o de radio. En realidad, hoy todos los campos de fuerza son parametrizados con los datos a emisión, porque es más fácil obtener estos datos y para la parametrización de campos de fuerzas necesitan miles y miles y más de miles de datos, ¿no? Porque tienen muchos parámetros, ¿ya? Y eso es el problema, ¿no? Y eso es la aventura de BioMD, porque para el BioMD tú no necesitas parámetros. Pero la desventaja es que necesito resolver esta ecuación de Schrödinger electrónica en cada paso. Eso es el problema. Okay, so everything which I have said until now is valid for every electronic structure method you can imagine. So you can use half-reform, you can use MP2, you can use coupled clusters, you can use CI. And all if you do this, you are limited to small systems. You're happy to do benzene or naphthalene, but you can't do C60, a full array. You can't do a system with 500 atoms. Yeah, and this is why quantum chemistry has suffered. So think about that. The first publication in quantum chemistry was 1926. The paper of Heitler and London to calculate the H2 molecule. And then quantum chemistry has suffered for at least 50 years to really do following up calculations that are in chemistry considered relevant. Yeah? Because if you think about at the end of the 60s, state-of-the-art quantum chemistry was the calculation of H2 with relativistic corrections. You might laugh, but this was at that time a very important calculation because it showed that quantum mechanics formulated in form of this Schrödinger equation is as precise as experiment can be. There was a dispute about spectral lines in the H2. There was measurements that did not fit with the calculations. And it was figured out that these discrepancies, which were few wave numbers, they were due to relativistic corrections in the H2 molecule. So at this time, this calculation was really relevant. But of course, for chemistry, H2 is really not of importance. Yeah?
This is a power computation problem. Like, let's say you're reading about quantum computing. I used the same method several years ago in a quantum this methodology.
Well, the problem really is that quantum computing can solve exponential scaling problems. The problem of quantum chemistry scales factorial. So even with a quantum computer and an algorithm based on this form, you will not be able to manage exactly the solution of the problem. What you can do with a quantum computer, however, is you can assign each electron in a molecule to a qubit. And so you basically make a picture of your real molecule in your quantum computer. And then, for example, you start with a starting vector. This what in the previous talk was shown there. This is a cat, Dirac cat. You start with a Dirac cat, and then you do simply the relaxation, this is quantum annealing, of this Dirac cat to the ground state, to the most stable structure. If you do this again, you don't get a fixed result. You must do this again and again and again and again, and then you get a statistic of results. And this statistic of results is your measurable quantity. Yeah. The problem is that the coherence time of such cats is very, very short at the moment. And so you can't really do this in this form. Yeah. So this is a problem. So I make now a jump from the late 60s to the 90s. And this gentleman here is Walter Kohn. He is a solid state, or he was unfortunately a solid state physicist who developed a methodology that was based on approximated methods very early developed in quantum chemistry. The so-called Thomas Fermi model was a model that was developed in the 30s, and it had a specific idea behind. And the idea behind was that people were not so much happy with the Schrödinger and Heisenberg picture, because as you have seen in the Schrödinger equation, most of the symbols in the Schrödinger equation are not real. They're not physical measurable symbols, not physical measurable quantities. So people said, could we not have real physics? Could we not have something like that the energy is calculated from some other physical, measurable, observable? And the idea was to use the density. But this was a model. And in fact, there is a paper in 1966 from Edward Teller, in which he and one of his students figured that yeah, so we will have some defect. Yeah, we will continue. Okay.
So we have a short commercial, short break, for tea break. We have 15 minutes and we will continue this workshop section.
Ah, ya.
Part 2 by the same professor. Yeah, thank you for coming once again, and we continue with the revolution in quantum chemistry, which takes or which carries the name density function theory. And as I told you, this goes back to the Thomas Fermi model in the 30s. And the idea is relative, actually, quite revolutionary, namely to say, does exist an expression for the energy in form of the density? So like that, I can say, okay, the energy is rho to the an integral over rho to the 2/3 or rho to the 5/3 or something like that. So does such an expression exist? I would like here only to point your emphasis here in the difference to the Schrödinger equation. Here in these simple equations, this is called an energy functional, where the energy is functional in form of the density. Yeah, so the idea is very simple. So you say the energy as functional of the density, let's say, is an integral rho from r to the 5/3 dr. This is a form. And the question is, does such a form exist? Does something like this really is real? And the intriguing point here is that both the density and the energy are physical observables. Yeah? And this is completely different to the concept of quantum mechanics as introduced by Schrödinger, where he uses an abstract model or space, let's say the Hilbert space, to obtain inside this Hilbert space some information about observables, but with quantities that are not observables by themselves. So here we have really direct connections between observables. And what Professor Kohn figured was the following. He said, okay, if something like this exists, then I must be able, with the knowledge of the density alone, to determine the electronic Hamilton operator of a molecule. Because if I can do this, I can map the density to this Hamilton operator, then I solve the Schrödinger equation. Okay, I solve the Schrödinger, but the point here is, I want to look if this exists. I don't want to look what is its form. This is an existence theorem, not a theorem that tells you something about the form. So then I have the electronic Hamilton operator. With this electronic Hamilton operator, I solve the Schrödinger equation and I obtain the energy. So is this possible? In other words, is it possible to obtain the electronic Hamilton operator from the information inside the density? Here you see a density of C2H2 acetylate. Okay, so let's start. What is the unknown? What are the unknowns in the electronic Hamilton operator? This is small n. This is the number of electrons. Capital C, which is the position of the nuclei, and ZC, which is the nuclear charge for each of these nuclei. So let's try to get the number of electrons. And the number of electrons we can simply get by integrating the density, right? So if I give you an n density, you integrate the density, you should get out an integer number. You give me the integer number back, then I know what is this small n in my electronic Hamilton operator. Yeah? So as the number of electrons I can directly obtain from the density. The next one is here, the position of the nuclei. This is this capital C, and if you look at the positions of the nuclei, the density bumps out. Yeah, it has extrema. So if I could touch the density every time when I feel, oh, there's something below me, oh, there's something below, oh, there's something below me, there is a nucleus. So I know I can, from the shape of the density, I can find these positions of the nucleus. And last but not least, you see from the altitude of these maxima in the density, I can, if I have a reference scale, I can say, oh yeah, this is in hydrogen, this is quite low. Oh yeah, this is in carbon, this is much, much higher. And for chemists, and also for physicists, I think, this is nothing really new. We are obtaining the structure of molecules by X-ray diffraction. This is a standard technique. This is nothing else as doing basically X-ray diffraction on the density. With this, I can obtain the form of the electronic Hamilton operator. And this is what Professor Kohn proved in a more mathematical way. Important here is to understand that this proof, which is called the Hohenberg-Kohn theorem, don't tell you anything of the form of this relation. It only tells you that this relation exists. It doesn't tell you how it looks like. It does not give you something like that. That would be, of course, great, but it doesn't do that. But already the existence theorem was good enough for a Nobel Prize. So I think if somebody can do this, there's another Nobel Prize. I'm pretty sure about that. And this is then the density mapping, where you can map the density on the number of electrons and the so-called external potential. This external potential is this term here, yeah, where you have the nuclear charge and the position of the charge. From here, you obtain the Schrödinger equation, you solve it, and you can show that indeed there must exist a functional relation between the energy of a molecule and the density. This thing really has revolutionized computational chemistry, because now people started to look at these functional relations. They started to develop approximated exchange correlation energy functionals, and it turned out that these calculations are much more accurate than corresponding Hartree-Fock calculations, using or having the same type of computational demand. So here you have something which has been also shown in the opening talk, that algorithmic development really has changed the way how a whole area of science is today done. And this is the reason why, if you look, when I was a PhD student and I started to go to conferences and talked about density functional theory, I usually was heavily attacked or thrown out of the room. Yeah, that was a reality. If you look today in the chemical literature, I would say that, and this is a very careful, very, let's say, loose estimate, that something like 90% of all quantum chemical calculations in chemistry are DFT-based calculations. Has anybody done here an MP2 calculation recently? Oh, that is my old guys, MP2, okay. So I'm careful now, I don't want to discredit MP2. But if you look at the results of MP2 calculations and you compare, for example, for organic molecules, this state-of-the-art hybrid calculation, MP2 has a hard state. That is simply a matter of fact. I mean, the modern hybrid calculations are in the accuracy range of coupled cluster, singles, doubles, parentheses, triples, which is the so-called gold standard for quantum chemistry. Yeah? And these are the hybrid calculations cost a fraction of the MP2 calculations. That is from the computational cost. So this is really a revolutionizing part in computational chemistry, and this is why we are now going everywhere to conferences like this, right? Because you have the hope that we might be able at a point to calculate your proteins. Well, as I said, careful with that, but QMMM, we might be able of that. Okay, so as I told in my description of this course is originally a hand-on session, and this means that usually people in the audience have the code, make the calculations, and we discuss the calculations. This all takes place in some nice places like here, but with a time frame of a week or so. So this is not what I can do here. So what I would like to do with you here is to show you some very simple calculations at an output. Okay, for some people here, as I understand, you have done such calculations already. This might be boring, but let me do it anyway for the people who don't know how such a calculation look like. I would like to start with an input. Where's my input? Input is here on this side. Okay. Yeah. So the most simple input you can imagine for D12K looks like this. Let me do this a little bit bigger. Okay, I think now it is more visible. So I have here a very small molecule, the carbon monoxide molecule. I choose this molecule for some reasonings I can show you later. And this is the input. So the information you have to provide to a quantum chemical program is the information, where are your nuclei in space? Note that you do not provide any information about the chemical bonding. There's nothing here in this input that says this carbon is bound to this oxygen, or this carbon is triple valent and this oxygen is triple valent, or this is double valent. All of that is not here necessary. The quantum chemical calculation, the only information you have to provide, so to speak, the minimum information, is the structure of the molecule you want to calculate. And now let us see what such a calculation yields when it runs. So this is the D1 output. So what you see here at the beginning as I said, the microphone is really an additional complication. What you see here at the beginning are general information. So we have molecular simulation data, and that is because D1 is quantum mechanics and molecular mechanics. So it might be here that you have some part is quantum mechanics, the other one is molecular mechanics. Here you see molecular simulation type is QM only. So this is a quantum mechanical calculation. You see the number of atoms, you see multiplicity. This is how many unpaired spins, to say it very sloppily, we have in the system. Multiplicity 1 means all spins are paired. A number of electrons, and then you see a lot of informations of the calculation. The next one, what the program does, is a point group symmetry analysis of the molecule. So in CO, you know this is C infinite V. This is what the program describes you here, that you have a symmetry of the nuclei. And then you get informations about basis set and so, but the most important point is in this part here. So this is what we call the self-consistent field calculation. This is an iterative solution of the electronic Schrödinger equation. Now, so this is iterative because the equation has been linearized in the so-called Rotan-Hall equation system. And this Rotan-Hall equation system is here solved again and again and again. And the most important point is the error. Most people only look at the error. The error goes nicely down. And when the error is down, at the end, there is a success. As they have converged, that means the electronic Schrödinger equation is solved, and then you get an output of the energy. And this is the energy which you have here. So the total energy is minus 112.44. What are this? 112.44. What is this for unit? What is this for unit? Kilocalories per mole, electron volts, wave numbers. Which unit has this energy you find at the end of such a quantum mechanical calculation? Huh? Kilojoules. 112 kilojoules per mole for the CO bond, you're a physicist, right? Okay. that keeps you safe. That keeps you safe. Otherwise, would be a problem. Okay. No, it's not kilojoules. Okay. So normally this would come, but you're not. I mean, I made the joke on you. I'm sorry. I'll do this again. Okay, but you are not so far away. I would say 95% of my students, they are all chemists in these classes, kilocalories per mole. 112 kilocalories per mole, CO maybe is not such a good calculation, but no, guys, this is far off, far off. These units, which you see here, they are, oops, what is this? Here it is. These units are so-called atomic units. And they are 112.44 atomic units. And an atomic unit has 627.27 kilocalories per mole. So this is enormous. This is outside of our energy scale in molecular physics, in chemistry, in any kind of who works with molecules, because this is energy for plasma or something like this, right? So this is astrophysics, elementary particle. So why do we get these kind of enormous energy? Well, the reason for that is we have solved the electronic Schrödinger equation quantum mechanically. Remember, our elementary particles are the electrons and the nuclei. The elementary particles in our particular CO calculations were 14 electrons, 1 C6 plus nucleus, and 1 O8 plus nucleus. So this complete fragmentation of these poor molecules into these particles is the energy that comes out of such a quantum chemical calculation. So why do I tell you this? Because this total energy is by itself useless. If you give me such a total energy, I say, so what? I change my basis set. I change my functional. I change anything in this calculation, and I get differences of half an atomic unit, easily. This has 300 kilocalories per mole. If this would be the accuracy of our calculations, I would be inaccurate. It's a joke to me. Okay? So, bottom line here is, if you do quantum chemical calculations, first principle calculations, the total energy that comes out is not of meaning. What is of meaning is something like this: dissociation energy or atomization energy. And in order to calculate the dissociation energy or an atomization energy, you always need to calculate the molecular energy and the energy of the atoms. And the difference of these energies, that is what is chemically, physically meaningful for us. And this difference then is really in the range of a few 100 kilocalories per mole, or a few hundred more by 4 kilojoules per mole. Yeah, but please do not interpret total energies from quantum chemical calculations. Okay? Yeah, good. Let me follow up here, and let me show you this in terms of another output one can obtain. And this is to obtain molecular orbitals. So if you think about the way of how to do calculations, what we use is called the linear combination of atomic orbitals. This is a very intuitive concept for chemists. You take your atom, for example, the carbon atom, you take your oxygen atom, and you have for the carbon atom atomic orbitals, you have for the oxygen atom atomic orbitals. You combine these atomic orbitals together, and these gives you such kind of molecular orbitals. And then these molecular orbitals do have sometimes strange symbols. Yeah. Also, for example, here 3A1 or 3 sigma. What is this meaning? What is this sigma meaning? From where does this sigma come? Or from where this A1? From where come these symbols here? The sigma star, the pi. What does these symbols mean? Students to the front. It's okay? No. They do not, they describe a kind, okay, my note was maybe a little bit too fast. One has to be careful here. They describe a kind of bonding that is true, but what they really describe is a symmetry these molecular orbitals have. And here's another connectivity. Yeah? If you make an input of the nuclei, and this input of the nuclei has a certain symmetry, in our case here C infinite V, and you solve the electronic Schrödinger equation, and the solution is consistent with your nuclear structure, then the symmetry of the electronic wave function must be identical to the symmetry the nuclei have. The reason for that is very deep in quantum mechanics, namely that the Hamilton operator and the symmetry operators commute with each other. Yeah? And this here actually is an assignment. This here is an assignment of this molecular orbital with respect to the symmetry. So then the gentleman here in front said, but they are showing chemical bonding. They show bond types. And stupid Andreas said no. But then he said, no, maybe I'm not so no. Also the no is not really a no. The no is not so wrong what you said actually. So let me show you this in terms also of a calculation. Let me see what I do have here. So I first show you a calculation that is an output that is easy to grab. So you know already the beginning. And here now you see an output where after the SCF convergence, you see the MO coefficients. Yeah? And what you see here is these are the MOs, MO1, 2, 3, 4, 5, and so on. This is the energy of the MOs. Again, this energy is in atomic units. Always when there is no labeling here in this code, it means atomic units. So we talk about large energies here. And then down here, you see the occupation. This molecular orbital occupied with 2 electrons, alpha and beta. No? 2, 2, 2, 2, 2, 2. And here is the breaking. This we call the HOMO, the highest occupied molecular orbital. And this we call the LUMO. And you see the LUMO, here are the energies of the LUMO. They are identical, they are degenerated. Yeah, this is why we have here the E1. And these labels A1, 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 this is a symmetry label. So these are symmetry adapted orbitals. If you now look at this, what you see is, oh yeah, this is yeah nice. The first molecular orbital, and then here I have, look, this is the 1s. Yeah, first molecular orbital is the 1s. Let's go back to our part here. Okay, this is the 1s. This is this orbital down here. Yeah, this is correct. This is A1 symmetry. Okay, this looks good. So now you see how molecular orbital diagrams are built. Okay, then you go to the second, boring. This is now the carbon 1s. And you go on. But now I want to show you this here, orbital number 5. Look at this energy, minus 0.3494, orbital number 6, minus 0.3494. They are also degenerated. And these orbitals, they have px, px, py, py. And this is what has been mentioned here, that we see different bond types. We see sigma bonding type, which is a bonding along an axis, and we see pi bonding type, which is perpendicular to the axis. We come in this in a second, because I show you something else. So this was a very simple basis set. This was called STO3G. This is minimal basis set. So you can use such an MO table and you can assign the molecular orbitals. The calculation, however, is catastrophically bad if you go to quantitative results. No. Okay. And here comes now a calculation that is much better in terms of the results. But it is a price to pay. These here are now still the molecular orbitals, and if you look at this, you will find the same number of molecular orbitals, but this calculation here has a lot of atomic orbitals. And this, what you see here, was one of the, or is one of the main problems in quantum chemistry. Mulliken sets this at a point. As more accurate the calculations become, as less intuitive the results are. So the concepts, the chemical concepts of bonding, of type of bonding, and so they, in Mulliken's word, evaporate to thin air. That was what he literally said about that. And this is a problem here. And how can we overcome such a problem? Well, modern computing makes it possible, because we can not only compute these molecular orbitals, but we also can visualize them. Let me do this here. Okay, good, does not work. Sorry for the visualization, does not work because the license is for some reasons not accessible. But okay, we can visualize this. I will show you examples on this. If you are interested, I can show you examples. But I would like to come here to another point, which is quite intriguing. And this is why I did the CO calculation. If you look in the chemical literature, you will find in many textbooks still today that the definition of the dipole moment direction is somehow vague or maybe even wrong. So there are textbooks in chemistry where the dipole direction is not from minus to plus, it is a physical direction, but opposite. So why is this so? And the reason for that was the CO molecule. So if you do the CO molecule and you do the calculation, you can calculate the charges on the carbon and on the oxygen. And you can use different models. I must say here that the charges of atoms in a molecule are not physical observables. Yeah? This is like if you think about the wave in the sea. You cannot simply cut the wave. If you cut the wave will make something different. So what we do when you define atomic charges in a molecule, you cut the wave function in one or the other way. That is something that is de facto not physically possible, but the demand for such atomic charges in chemistry is so large, is so high, that there are many, many models to calculate such charges, and I have here listed a few of them. And what is common to all of these models is that if you look at the CO, the carbon is positively charged and the oxygen is negatively charged. And if you now ask a chemist, will say, oh, this is really boring. I look in my periodic table and I think about electronegativity. Now, of course, oxygen is more electronegative than carbon. So that is how it should look like. Correct. But then you calculate the dipole moment of the CO molecule. And the problem here is really you calculate the dipole moment of the CO molecule with a low order wave function method. This is not MP2 to emphasize that MP2 calculations are good calculations, but for example, with Hartley Fock, and the dipole moment will go in the wrong direction. It will look something like this. But if you calculate the dipole moment, for example, with density functional theory or with a high order wave function method, you find something like this. The dipole moment points from the carbon to the oxygen. If you follow these, that means the carbon must be negative and the oxygen must be positive. Huh? This is against electronegativity concept. This is against everything you learn in chemistry 01. So what is going on here? And this really has caused the community 1 decade to figure this out. The issue is that in carbon monoxide, you do have a very strange electron distribution, which you can best visualize with the molecular electrostatic potential. You have a huge part of electrons behind the carbon. Yeah, this is this blue part here, and this gives rise to a negative electrostatic potential. This is a lone pair. And you also have a lone pair behind the oxygen, but this lone pair is much smaller. So the charge moment is in fact according to the electronegativity. This is a green moment here. So the charge moment points from the oxygen to the carbon. But now the charge is not localized in the position of the carbon or in the position of the oxygen, but it is anisotropically distributed around these atoms. And so there are so-called hybrid moments. There are hybrid moments for the carbon and there are hybrid moments for the oxygen. And the crazy thing in CO is that the hybrid moment for the carbon is larger than the charge moment and the hybrid moment for the oxygen together. So this gives rise to, at the first moment, a completely perplexed situation in this molecule. But you can resolve this, and this is an example that there is always something like a rational design or a rational answer for such things. And indeed, then, if you add these moments together, you get these, it's the first instance contradictory dipole moment of the carbon monoxide. Okay, are there questions at this point here? No? Everything as it should be? Everyone happy?
One question.
Yeah, sure.
We would like to know why the energy values are negative.
Because the energy of a molecule is more negative than the energy of the atoms. Yeah, so if you look at this, for example, the atomization reaction which you have with CO goes over in the carbon. This is a triplet plus the carbon of the oxygen. So if you now calculate the binding energy, the delta E, I know why you asked it. Okay, I come to you in a moment. So in this chemical reaction, you have product energies. So you have energy of the carbon triplet plus the energy of the oxygen triplet minus the energy of the CO. Yeah. So now you can read this equation from two sides. You can read it from right to left or from left to right. So sometimes the binding energies are reported positive, sometimes the binding energies are reported negative. In chemistry, the let's say the common way is negative. I know in physics that their binding energies often reported in positive numbers. Yeah, there you have to be careful. True. Okay. Other questions? No? Yeah, please. Oh, yeah, okay. Yeah, in fact, I agree. You're right. If you use here different charges, so for example, ESP charges, as you said, because they come from the electrostatic potential, the ESP charges might be opposite. I really don't know. I have not calculated them. But the point is that also there, the issue is really, if you concentrate all the charge in the atom, in the model, you have a problem because the charge is anisotropically distributed around the atom. So basically, you need somehow to put in these dipole moments that arise from the atoms. So if you have a charge analysis that incorporates these dipole moments, then definitely you will get the right qualitative picture. I mean, I have here, I didn't list it here, Löfting population analysis, because actually Löfting population analysis gives the carbon negative and the oxygen positive, but this is an artifact from the population analysis. That is not an insight into the electronic distribution in this molecule. So with this charge analysis, you should be always really careful. Also, qualitatively discussion is okay, but it is always good if you have charge analysis backed up by something that is more covered by observable. So I would say if you have electrostatic potential plus charge analysis, you have really a possibility to understand the bonding and the electron distribution in the system. Otherwise, if you only look at these numbers, which one do you use? Okay. Other question? Okay, good. So then I would like to briefly go to something else, and that is what is called topological analysis, and it has something to do also with an interpretation. You have always to think about that what I'm talking in the moment, also with the charges, with the atomic charges, and also with this topological analysis, these are interpretations of the calculation. These are not observables. These are not experimentally verifiable numbers. Nevertheless, these models are of really big importance if you do chemistry. So if you think about where is the CO, coming back to the CO, where is the CO, or how is the CO absorbing on a surface? Yeah, how is an absorption of CO on a surface? Then if you have an absorption, for example, on MgO, then this lone pair here is dominant, and the CO will absorb on the surface with the carbon down directly on top of the magnesium. Yeah, and you can say already, this is not absorbing on the oxygen, it's absorbing on the magnesium. So these very simple concepts are really of great help for chemistry, for making qualitative predictions. Sorry for that. So another thing is, what is the bonding in a molecule? That is a fundamental question very often asked by chemists when they see a molecule. And here, for example, this is a chromium atom bond onto an aromat. This is a benzene ring here. And here's a four-membered ring. Also benzodiketon is this here. And if you look at these bondings, then this is something you would obtain, let's say, from a standard software. And the bonding is done on the basis of the distances between the atoms. But if you look at the electron density of the system, and you now look at the topology of the electron density, you can find in these topologies so-called bond critical points. These bond critical points, again, they are observables, but it is not an observable that a bond critical point is really a critical point for a bond. This, again, is an interpretation. But nevertheless, the topology of the density is not the same as the topology from such a distant criteria. And what you can see here is that the chromium atom does not bind equivalent to all the 6 carbon atoms here of the benzene ring, but it has a preferred binding here to 3 carbons. And actually here, unfortunately, I cannot show you this in better detail, but here you see a kind of symmetry breaking in the topology of the density. That means that this molecule somehow is sensitive to the accuracy of the structure optimization you are performing here. Yeah? And this was not perfectly well optimized in CS symmetry. Otherwise, these bond criteria, so this bond pass here should end up in this bond critical point up here. Yeah. So you see that with such analysis, again, it does not give you a hard quantitative number, but it gives you information about the stability of your molecule in terms of changes in the structure. It gives you information of maybe that not all of these carbon atoms are the same. If you combine this with charge analysis, with population analysis, with valence analysis, you obtain a picture that hopefully at a point becomes consistent. This can become really strange, really strange. And this is when you come to metal clusters. This is Le5, and that is the structure of Le5, again on a bond distance criteria. And that is the structure of Le5 in the topology of the density. And what you see here is that these gray points usually are atoms. But if you count 1, 2, 3, 4, 5, 6, 7, you have too many atoms. These are so-called non-nuclear attractors. These are small bumps in the density which you have that are not at the position of an atom. This is one of the reasons why if you ask a chemist about alkali metals, then you can say, sodium, potassium, yeah, this is more or less the same. What is with lithium? Yeah, no. As a lithium is somehow a little bit different. Lithium behaves really different to sodium or to potassium. For example, if you think about lithium organelles, if you want to do carbon cations in organic chemistry, you do this over lithium organelles. Why do you use lithium organelles and not sodium organelles? Because lithium is much stronger to attract, to give the electrons away. And the electron density that is given away from such lithium clusters are electron densities that is here in the system. So lithium is really a strong electron donor, much stronger than, for example, sodium or potassium. Yeah. And this is, again, I mean, by itself, this is not something that is conclusive, but in combination with other also observables, you obtain a consistent picture. So these are models that are coming out of quantum chemical calculations. And that is today a very big business, at least in chemistry.
This is why batteries for lithium is better.
No, I think that battery is also
In the audience, there is a question. It's because lithium batteries are better.
really differences in observables and polarizabilities. If you compare lithium polarizabilities with sodium polarizabilities, that would be very strange. What should we explain? Okay, other questions?
Otra pregunta de la audiencia. How do you construct these topologies from the calculations from Demon?
This comes directly out of D1. You put it into the visualization program and you can get these pictures. Another selling. This is selling event. Wrong. Again, it's the wrong audience. Okay, let me bring you to something else, and I would like to. How much time do I have?
I was going to ask if there is an experimental picture of the density of these structures.
Experimentally is really, really difficult. The only way you can get this is by neutron diffraction. So neutron diffraction, you can directly measure the density in these, also in compounds, but you need crystals for that, not gas phase. And there are, in fact, also I know that in Brooklyn, in Brooklyn is this laboratory, right? They do have people, I forgot the name, there is a crystallograph who measures the density with neutron diffraction and then uses this technology, this topological analysis for the measured density, also for the measured densities. Yeah, okay. This is possible in principle.
Okay.
Okay.
Thank you.
Okay. Now I would like to come here to something which is to show you danger in your calculation. Danger in your calculation. Okay. Let's take something very simple. We take water. And one thinks that one can do nothing wrong, right? When I show this to people, they say, what to the heck you can do wrong with the water calculation? Is it possible to do something wrong with water? But this is here, I show you in input. No, moment, I want to show you output. Okay. Okay, so this is a water molecule. I took a 90 degrees angle. This is a geometry optimization. Yeah, so this is, we go along the potential energy surface. This is now, here's the starting point, and then we go down to the minimum. Oops. This is also given up. Okay, minimum is up to here. And we let this run. And it's simple. I mean, the water makes a little plop. And you get the water ground state as you would expect. So here you do have an angle of around 104 degrees. One distance, oxygen, hydrogen is around an angstrom. So everything fine as you want to have it. Okay. Now, let us do this different. And I strongly recommend, if you do have a program available by yourself, this is not the right thing. If you do have a program available by yourself, any program you want to use, do the same experiments that I do here. So now I give an input where the water structure, battery has given up on this, where the water structure is linear. Hydrogen, oxygen, hydrogen. So I have an exact linear structure. So I must really have exactly 180 degrees, not 179.9, exactly 180 degrees. And I do this optimization again. And if you look at the picture, it looks also fine. The energy goes down. But the structure remains linear. Yeah. The reason for that is that if you have a linear structure that is exactly 180 degrees, the gradients that you have here for the deformation are in both sides exactly the same. So if you are in your input by some reasoning introduce a certain kind of symmetry, it can be that the system is trapped in this symmetry. And then you optimize, you get an energy, and you say, ah, yes, I have it. It's completely wrong. It's completely wrong. So this is done with, I did this in Viva with Cartesian coordinates, I did this with redundant coordinates. Okay, if you could change it. Thank you so much. So I did this with Cartesian coordinates, I did this with redundant coordinates. I think you can do this with any kind of coordinates you want. You see, linear is the energy much higher, much higher. And okay, there is one problem that is particularly bad. Okay, it starts with G and ends with Aussehen. It really makes this regular. You give something in a certain point group and it optimizes you the structure in this point group, but it does not optimize you the structure but it does not optimize you the structure to really the local minimum. Yeah? So be very careful. If Gaussian tells you, oh, this is C2V or this is D2H, that means alarm, move an atom away so that D2H or C2V is no longer fulfilled. And then let it run to the optimization. So let's assume you don't know anything about this system. This is not in water, but let's assume, we end up here in this part. And so how do we figure that this is not really a minimum? And the answer is, and I skip here my LE2O, which is a very nice example, but the answer is here. What you need to do, and this is something you need to do in any kind of structure optimization. If you make a structure optimization and you don't do a frequency analysis, I don't believe you. So easy it is. Structure optimization without frequency analysis do not count. Frequency analysis calculates the second derivatives. So you need always, after the structure optimization, to calculate these kind of second derivatives. And if you calculate the second derivatives, you can obtain the so-called normal modes by the diagonalization of the Hessian matrix. And if all these normal modes are positive, yes, you have optimized to a minimum, and I believe you. And if you have imaginary normal modes, like here, you have not a minimum. And the nice thing on the Hessian matrix calculation is that once you have done this and you end up with this thing, you can use this Hessian, and now you can redo the calculation, you make a restart of your calculation, and in this case also this linear structure, because now you have second order information, will converge in the optimization to this structure. But it is really important for structure optimization always to confirm that you do have minima, or if you search transition states, that you have transition states. Okay, good. Questions to this? No? Yeah, please. Yeah. In Demon you can also give no sim, but this was done without symmetry. So if you even without symmetry, if you give the water really linear, it stays linear. If it doesn't stay linear, your gradients are in. Yeah, this is something which you can do, of course.
These minimizations are performed using the second derivatives in Demon.
You can do this, I have not done, of course. And then this will not happen. But if you need to have the Hessian, the start Hessian calculate. Then you're fine. You're fine. At least you are fine for the next steps. Because if you only calculate the start Hessian, then during the optimization you make an update. Usually you do a BFGS update, and you have to realize that the BFGS update is an approximation. So, for example, you start with a start Hessian that has two imaginary frequencies. And then the optimizer will say, I know the directions in which I have to go in order to avoid these imaginary frequencies. And you will go in these directions. You will do things right. But in the next step, if you don't ask for recalculating the Hessian, then the Hessian is updated with BFGS. And the BFGS update is an approximation. And then you approximate the Hessian and you get another frequency, also another eigenvalue spectrum. And for example, after some steps, with the BFGS update, your eigenvalue spectrum is positive. And then the optimizer will say, okay, I'm done, this is a minimum. And if you then do a frequency analysis, it is possible that, for example, one of the imaginary frequencies has survived. In order to avoid that, you would need to calculate the Hessian in each optimization step explicitly. So you have to switch from quasi-Newton to Newton. In that moment, then you are guaranteed to have optimization to local minimum. Okay? Very good question. Thanks to you. Okay, excellent. More questions? Good. So now let's come to the next challenge. We become a little bit more complicated now. Transition states. So we want to find transition states. Again, I make very, very simple reactions here. So in very simple reactions, you use chemical intuition. You have an idea how the transition state is. But already when I get the system a little bit more complicated, then you will not know how the transition state looks like. So how do you find transition states? So there are in the literature basically two methods which I know that are really working. One is called nudged elastic band, and the other one is settle. And the settle method is what we have in DEMON, and this is what the settle method does. You have, for the transition state search, you have your reactant, you have your product, you construct the distance between them, and then you build such a hypersphere here around the reactant, and you optimize on this hypersphere. And when you do this optimization on the hypersphere, you find the point on these bond paths, if everything goes well, and if your implementation is correct. And this is a big issue with this method, because the implementation is most often not correct. And then you can go further on, and in this way you can go up to the region where you have the transition state. Both methods, nudged elastic band and settle, do not find in the current implementation the transition state. They find always points that are close to the transition state, but these are not the transition state. So you have then, with these points, to do an eigenvector following to the transition state to really, really find the transition state. Yeah, so you are not finished with nudged elastic band, neither you are finished with settle. You have to do the transition state optimization from the starting point you obtain from this method. That is very, very important to realize. So let me show you how something like this works in practice. And I do have here do not have this. I have the ERC. Where's my transition state finding? Ah, the settle, there it is. It's an own directory. Okay, here is settle. And I would like to show you an output. Oh, this is the settle. This is the settle interpolation. So here you see an HCN, and the interpolation is between HCN and CNH. So this is the most simple rearrangement reaction you can find. And if you look now here, this here is the output of a settle interpolation. And you see that if you look to find something that looks very similar to the transition state. And if you do a frequency analysis of the structure, you find one imaginary frequency. So it's very tempting to say this is a transition state, but it is not true. It is actually a little bit too high. The transition state by itself is below. Yeah, from here, you need to do the transition state search explicitly. And this is done in the next kind of calculation. Oh, this was a wrong input. No, where is it? No, it's a 3 in front. Here we go. So this is a starting structure. And if you now do the optimization, you see that you still do a small movement. You start from here and you do the small movement. This is not a lot, but it depends on the complexity of the transition state, how much energy change you have here. And if you now look at the normal modes, you see that you have here the first normal mode, which is the transition state mode for these rearrangement reactions. So it's very important that when you search really transition states for reactions, that you do have a two-step procedure. The first step is to come close to the transition state into the region where the Hessian matrix has a negative eigenvalue. And then you follow the corresponding eigenvector, this is called eigenvector following, up really to the transition state. This is usually a difference of 2-3 kilocalories per mole, which you have compared to the interpolated part of the transition state. And there's very often people stop at the interpolation. And you know, in transition state theory, you have Arrhenius equation, the activation energy goes exponentially in the rate constant. So 2-3 kilocalorie difference in the transition state for the rate constant are 2 orders of magnitude. So it's a non-negligible amount. Okay, so this is what I have here for these transition state search. Yeah.
For the optimization of the hypersphere, the selection of the gradients, how should be?
Becomes smaller and smaller and smaller. So you start basically with shrinking the distance between the reactant and product by, for example, 2/3. Then you optimize, and then for the next radius you reduce again by 2/3. And so in this way you move up on the minimum energy paths. Exactly. So like if you climb up a mountain.
For instance, when you have these transitions,
we change temperature or introduce energy somehow. How do you manage that?
Everything's zero K. Okay. In the moment, this is a very good question. Actually, I put this in here. Very often people put in here some delta G, right? If you look in textbooks or you find the free energies, they don't tell you how to calculate the delta G. They simply draw it on this picture. If you want really to get free energy calculations, you are coming into a really new ballgame. So that is something we are just now developing. And that is where you have to combine this kind of methodology I have here with some kind of molecular dynamics. Yeah? And I will show you an example. Do you tell me how much time I have? Because I'm. How much? 1 hour. Another hour?
Yeah, you asked for 3 hours.
Oh, wow. If I have another hour, I was rushing here through it, and now I have another hour. Oh, that is Okay, now we are talking. I'm not used to this. Usually I'm kicked out from the front very soon. Okay, no, I'm happy. I mean, this is really good news. So I can do a lot of things now, which I can show you. If you give me some moments, and also I will activate again here the visualization program to show you directly what we can do with the visualization. Okay, also in the moment we are going into this part, then we need basically to select which degrees of freedom in a system are molecular dynamics degrees of freedom, and which degrees of freedom are such kind of optimization, transition state finding degrees of freedom. Yeah, we need to have this selection, and this is particularly easy if you think, and that is where we start with, of course, if you think about reactions in solutions. Then a good approximation is that you say, okay, I have my reactant, and my reactants, they are quantum mechanical, and my solutions around are molecular mechanical. Or a few solution molecules are also quantum mechanical, and the rest of the solution molecules are molecular mechanics. And if you do this, then you can introduce the concept of so-called free energy gradients. So what is a free energy gradient? So that is, if you think about that, something to clean here, because otherwise I have too much. So if not, I have some paper. No problem, no problem. Is that right? Easy to do. Okay. Let me set this up because this is really interesting in the following way. So you have a system, let's say, a chemical reaction where you have a nucleophilic attack somewhere here, and this system you calculate quantum mechanically, and this is in water. This water that you have here in the surrounding, this is NM water. This is molecular mechanics. Now, what you can do is you can run a molecular dynamics of CMM. And this molecular dynamics of CMM will change the positions of the waters. And now these positions of the water change will influence the gradients you are calculating here. And so what you will do is you will obtain gradients here with respect to QM atoms, but you sample these gradients with respect to the MMD. And these quantities are called free energy gradients. And with these quantity, with the free energy gradients, you can combine the type of calculations I have shown here with the molecular dynamics of the surrounding, and then we are talking about free energies. And that is really where we go with this kind of development. That is one development that is in the moment active in Silvester, and as usual, we are searching volunteers to help us in the development, of course. Good. Yeah, because I have time, I have the possibility also to go maybe a little bit back here, because then I can show you something what I wanted to show you here. Yeah, here's an issue which I would like to make. Also, we have discussed this water problem, and we have seen that this was the problem of the preparation of the input with all what belongs to it. No? So I have made an input. The water is absolutely linear, 180 degrees. I have not calculated the Hessian matrix at the beginning of the input. So I have made this so that indeed the water optimization remains linear. Now, I substitute in the water the hydrogen by lithium. So I calculate Le2O. And this is what you see here as input structure. And then you do this, so these points here, these spheres are lithium atoms, and you can optimize which whatever you want also. This becomes really linear. And it is not an accident that here these distances are much larger than the distances here in the water molecules. Yeah, that is typical for lithium. Lithium makes really large distances. And that is also when you have lithium organelles. We just now work on a chemical reaction that one of our colleagues did in the laboratory. And he has big problems to understand the result of this chemical reaction, and it is with a lithium organelle. And it is a reaction he does inside THF, tetrahydrofuran. And he calculated by himself the transition states and all that, and he did this very, very good. And all these results did not tell him anything about why he sees this product distribution. And we then did the molecular dynamics of the system, and we incorporated the THF. And what we saw was that two THF molecules were like chelate complexes going with the oxygen onto the lithium. And they are protecting the lithium from the reactant. And this is the reason why you see a different product distribution. So here you really see that if you make a reaction in different solvents, you can get qualitative different results. And that is something how you can tune reactions. And that is what we want to be able to quantitatively predict with the free energy gradients. Yeah, that we can understand the solvent effect on reaction product distribution. So anyway, I mean, here you see that this is linear, and of course, after the water, you might wonder, is this really a minimum? And you do again the frequency analysis. And what you see here for the frequency analysis is all modes are positive. So now I have a question. I have water, 3 atoms, and I see 1, 2, 3 normal modes. And I have Ne2O, 3 atoms, and I see 1, 2, 3, 4 normal modes. Why is this? Why has a molecule with the same number of atoms different numbers of normal modes? Exactly. Okay, that's the answer. It's linear. Because of the linearity, remember you have the internal degrees of freedom is 3n minus 3n minus, no, not minus 1, come on. 3n times the number of atoms minus 6. These are the internal degrees of freedom. So if you look for the water, 3 times 3 is 9, minus 6 is 3. So that is what we see here. But for linear molecules, you have 3n atom minus 5. Because 1 degree of freedom, because it's linear, cannot store energy. Remember, for the energy storage, you need a radius, but if the molecule is linear in this direction, it does not have a radius. So this degree of freedom cannot store energy. So you lose an external degree of freedom, and you recover for that an internal degree of freedom. And this internal degree of freedom always goes with a degeneracy. Yeah? And this degeneracy there, if you look in spectroscopy, is very famous for the so-called Renner effect. There you see something like a Young-Teller effect for linear molecules, namely in the vibrational spectrum, in the anharmonicity, these two frequencies split up. And that is called the Renner effect. So that is the Young-Teller effect for linear molecules. Okay, good. So, but we were at the reaction, and what I wanted to show you is, so once you did this, you did the transition state finding, so you do have the starting points. So you have the HCN, this is your product. You have the HNC, this is your reactant. And you have done the subtle interpolation, you got the starting point, and then from here, you did the transition state search. Then what you find here is the transition state geometry. You see, these are normal modes of the HNC, all positive. This is a minimum, degeneracy is here. Everything fine. HCN, C infinite B again. Degeneracy here, everything is positive. Now, one thing you can obtain from such kind of molecular simulations is an assignment of the vibrations according to certain movements. You can see this here. So for example, we see these frequencies which we have there. It's a little bit more in this direction. Oops, this was not good. So. Okay. So we have here the molecule. And we have here a vibration. Makes this vibration a little bit slower. Doesn't look so nervous. And you see, this is a hydrogen vibration. Yeah, this is a hydrogen bending. You see here, and if you look at the next vibration, this is degenerated. You can already imagine where the other vibrations. Yeah, you see the degeneracy of these two vibrations, and this is where you can obtain relative easily the assignment. This one is hydrogen bending. Yeah? Because if you do, for example, in spectrum, you only see signals at certain kind of wave numbers. You do not, the spectrum does not tell you which kind of normal mode corresponds to this signal. So with this simulation, you can assign these to movements. Yeah, and if you look here at the higher vibrations, you see you have here the CN stretch vibration, and even higher you have the hydrogen stretching. Yeah, and so this is a very convenient way to assign spectra. One has to say here that the frequencies that are calculated, they are not so accurate. And the reason for that is not the electronic structure method. The reason is the way the frequencies are calculated, because what is used is the so-called double harmonic approximation. So you assume an harmonic potential. Yeah, so for the frequency analysis, you assume that your potential energy surface at the minimum has a harmonic shape. So you assume something that is rather harmonic here, it goes up here, and then you calculate the frequencies, and here's your equilibrium distance, and you obtain here the vibrational mode. Yeah, but the reality, unfortunately, looks most often quite different. You do have anharmonicities there, and at least for main group elements, the harmonicity is not so large that you have really deviations down here, but you do have severe deviations or changes in your vibrational modes and in the corresponding vibrational energy. Yeah? And this anharmonicity correction is not included in this calculation. So for this reason, the accuracy of the frequencies which you see here, they are only in the range of, let's say, 20 to 50 wave numbers. So they are not good enough to really assign a vibrational spectrum. But they are good enough to assign the normal modes to the spectrum usually. That is, at least to the main normal modes to the spectrum. So if you do this calculation, you have calculated the reactant, you have calculated the product, and you make the energy difference. What you get here out, this energy difference between these two energies, you see again, this is atomic units, these are huge numbers. Here I have translated this energy difference into kilocalories per mole, and this is the reaction energy. Yeah, from the energy difference between the reaction and the product. And when you now use different electronic structure methods, as for example, one person wants to calculate MP2, this kind of reaction, another person wants to calculate the speed 3 look, another person wants to calculate it with M06, and so on. These total numbers here, they will change. And they will change substantially. They will change by half an atomic unit. So you cannot compare these total energies here between different electronic structure methods. But what you can compare is this difference energy. This difference energy is the result that is comparable, and you will see if you use a certain level of theory, then you get here more or less a convergence to this number. And that is what you can obtain from such kind of calculation. Okay, now you have the transition state, you have the reactant, and you have the product. And now comes the question, are you finished? Is this the reaction completely described? It's a 50-50 answer, yes or no. So that's a good question for students. So what do you think? You have the reactant, it's a minimum, you have the energy, you have the product, it's a minimum, you have the energy, you have the reaction energy, and you have the transition state. Is with this the reaction completely described? Hmm? Come on. Don't let me stand there so low. What you said, yes? What is this? Yeah, what now? Yes or no? No, exactly. Would that be also too easy, right? Exactly. Of course not. So why is the reaction not completely described? What could happen? I mean, you have got everything. And so if you think about that here in this form, you have here the energy, here's the reaction coordinate, here's the reactant, here's the product, and here's the transition state. You have to have everything. What could happen? Why is this not sufficient to say, okay, now the reaction is elucidated? What is missed? Yeah? Yeah? Everybody. Okay? Okay, I would make, okay, everything is fine. Everything is fine. So, but the doctor said, no, because someone, well, the point could be, that there is an intermediate, right? And there can be not only one intermediate, there can be many intermediates. So what we learn from that, even if we have the transition state, we are still not finished with the elucidation of our reaction. So the next step is really that we calculate the reaction coordinates, that we really calculate how the reaction proceeds from the reactant to the product. So to this end, we have the calculation of the so-called intrinsic reaction coordinate. Yeah? And this is something I show you here, how to do this also. And I have it outside here. Okay. Situation of the intrinsic reaction coordinate is always in such a way that we start at the transition state. Yeah? So we start here at this point, and we have two directions, two fundamental directions. And these fundamental directions are given by the imaginary frequency directions. So that is the negative eigenvalue of the Hessian matrix. Remember, the transition state is one negative eigenvalue of the Hessian matrix. This negative eigenvalue of the Hessian matrix has an eigenvector. And this eigenvector is here. And this eigenvector can be searched in two directions, forward and reverse. Yeah? And this is exactly what we have to do in order to find the intrinsic reaction coordinate. And this here is the ERC calculation for the HCN from one side. This here is this structure. This is the transition state structure. And this down here, if we have resolved the reaction, this must be either HCN or CNH. If this becomes something different, then we have an intermediate. Yeah? And we can run this. And we see it is linear. So there's no intermediate here. The reaction is very simple. And we can do this over both sides, also reactant and product. We can glue this then together. And when we do this, we obtain here the full ERC path. And that is how it now looks like. Let's make it a little bit slower. Yeah, now this is how you see the reaction. And you see that the reaction indeed proceeds from the reactant we have thought of to the product we have thought of. So this reaction is completely resolved. Yeah? This, for more complicated reactions, this is, however, not always the case. So here's the resolution for our situation. Here's our reactant, here's our product, here's our transition state. We have characterized the transition state. It has one imaginary frequency. If you look in the Gaussian output, and also if you look in the Riemann output, this frequency is denoted by a minus sign, usually. And that has resulted in generations of students that call these frequencies negative. Okay, so there's nothing like a negative frequency. Now, if you think about the frequency, the nu is proportional to k over n. N is always positive, it's a mass. And k is the force constant. This is the second derivative of the energy with respect to atomic coordinates. Yeah? And this second derivative can be positive or negative. And so when you have the second derivative negative, you have this negative number under the square root, and this gives you an imaginary frequency. This is why, please, in your PhD defense or in your next exam also, please talk about imaginary frequencies and avoid the term negative frequencies. Yeah? If you want to get me crazy, that is one possibility to get me crazy. If somebody says negative frequencies. So we have these characterized reactant, product, transition state. And now from this picture, we can calculate the reaction energy is here. We can calculate the activation energy is here. So we have information about the thermodynamic of the reaction and about the kinetic of the reaction. Now what is missed here is the temperature. And we can introduce the temperature actually in a model. This is also a harmonic model in the same spirit as the double harmonic model approximation used for the frequencies. And then we can get here temperature corrections. That is rather straightforward. And that can be obtained by frequency analysis of these three characteristic structures on the potential energy surface. This is, of course, completely harmonic. If you want to go non-harmonic, then you have to go to this new development of free energy gradients, where just only a few groups in the world are working, maybe 10 or 15. So I show you now an example where the situation was not so simple. And this is an example where we put quite a bit of time into it when we resolved it. This is a Diels-Alder reaction. So what is a Diels-Alder reaction? The Diels-Alder reaction is a symmetry-controlled reaction of the type where you have here a so-called diene. In our case, the diene is a fluorane, so it has here a bridge. And you have here an enophile. And the reaction is a skipping of bonds, which then ends up into a structure of this form with a double bond down here. And this is symmetry controlled, and it is believed that the pi system is mainly responsible for this reaction. And so if you do have here a substituent who could interact with the pi system up here, you call this endo, and from these so-called Woodward-Hoffmann rules, it is believed that the endo product is the preferred product. Yeah? And this holds for many, many reactions, but it doesn't hold for this reaction. So here is the double bond, here's the other double bond of the diene, here's the double bond of the enophile, and here's an oxygen atom that has p orbitals that could interact actually with these diene here. And so you would expect that this endo product is a preferred product and the exo product is not. But if you do the experiment, you see that the product distribution is just reversed. You have 1 to 19, so 1 endo to 19 exo. So exo is clearly preferred. And then you ask yourself, why is this so? And you calculate, for example, the energies of the reactant and of the product, and you see that these energies are basically the same. One is 2.5 kilocalories per mole above the reactant, the other one is 2.6 kilocalories per mole over the reactant. So this is an endothermic or endogenic reaction, and this is the reason why you have to do this reaction under pressure in order to drive the reaction from the reactant to the product. But this is not the problem. This does not say why this rule is not fulfilled. So then you say, okay, probably the barriers, the activation barriers. So you calculate the activation barriers. And when you calculate the activation barriers, the result is very disappointing. 21.3 on this side, 21.5. Yeah, 21.3 kilocalories per mole on this side, 21.5 kilocalories on this side. The difference is 0.2 kilocalories per mole. This difference cannot be responsible for this product distribution. So, and then you calculate the ERC, and then you see something that is really interesting, namely the ERC of this transition state here, which goes to the endo product, ends up in the nirvana. It does not bring you back to the reactor. So clearly here is a problem with an intermediate. So you take this structure from the ERC calculation and you optimize this, and you see here that you have another conformer that is a conformer, we call them exo and endo. This is the original reactant that has been given into the reaction, but this here is a conformer which is needed in order to go to the endo product. And then, of course, you do have a transition state between these two conformers, between the endo and the exo. This is a rotational transition state. And the important point now is that this rotational transition state is much lower in energy than your activation barrier. That means if you have a reaction condition where you go over these barriers, this system here is in equilibrium, because you certainly can go over this transition state. And if you now calculate the equilibrium constant in gas phase with a crude harmonic model between these two guys, the exo and the endo reactant, you find a relation of 1 to 16, which is, I would say, very good and qualitative agreement with the experimental observation. Yeah, and so this is something which is really a warning when you resolve more complicated reactions. Yeah, it is important to find the transition state. Of course, the first thing, it is important to find the reactant and the product. It is important to find the transition state, but it is also important then to verify that the found transition state is really the transition state for the reactant and products you have considered, and not that you have intermediates in between. And if you have something like this, it would be nice if you read this Jack's paper. This is old, but if you read this Jack's paper and you read what the authors are saying, why you have here this endo-exo relation, no comments. They have discussed this over 2 or 3 pages. It has nothing to do with reality. There is simply an equilibrium in between. That's all what there is. So what I want to point out here, search for the simple but true. Search for the simple truth. Do not be satisfied because in some publications, some big shot says, this is so and so, this is so and so. If you do not find that this makes for you rational sense, if you say, I do not understand this, and you really try hard and you do it again and you don't understand, then you talk to your friends, you talk to your classmates, to your colleagues, and if none of you understands what is going on, then it's a good idea to do a research. That's really, really important. I mean, trust yourself. That is what I want to tell you. Okay, good. Questions to this? Not that you get me wrong. In 90% of all the cases, you make your calculation, everything was fine. This here is a collection of pathological, of things. Either I have made it wrong, or it's not so that this is a rule. No, these are the exceptions. This is really a sammelsurium of exceptions. But be prepared that such exceptions exist in your calculation. No? And it's not sufficient to simply do the calculation and to bring the molecules or the reactions through the computer. But this is not sufficient. You really must put it into the perspective of what you're looking for. Yes.
There are very few programs that can calculate this with considering pressure. We can use pressure or consider pressure with Demon.
Not yet. We are working on it. This is the current work of a PhD student of mine, and it's not easy. But yeah, we will try to do this with pressure. Absolutely. Very good question.
Okay, thank you.
Excellent question. What I wanted to say here in general is, before I come to my last part, let me go to my first slide. Okay, also, I jumped a little bit over this because of time. This is my email address. I have, for this kind of presentation, for this hand-on session, I have 2 review articles that are also basically discussing the electronic structure problem we have discussed. Yeah? One is a review article in, I think it's Encyclopedia of Physical Organic Chemistry or so, and the other is a review article in some computational chemistry book. The books are quite expensive, but if you're really interested in this, and particularly if you're interested in the theoretical background and in ADFT, write me an email and I send you these reviews, okay? So, and of course, I'm always open for questions and discussions with pleasure. Okay. So, this here. Okay. So now my last one, which I have, is about molecular dynamics. And it is actually molecular dynamics in terms of quantum systems alone and in terms of QMMM. And we will look at these inputs a little bit in detail, particularly in QMMM. By the way, pressure we will introduce by QMMM. The pressure is done by the MM environment in QMMM calculations. And our toy molecule is glycine. Glycine is the most simple amino acid. As you know, amino acids can exist in two forms. In the neutral form, so where you have protonated here the carboxyl group, then you have here the amine group, the NH2, and it can exist in its zwilling form, where you have here an NH3 plus group and negative charge down here on the carboxylate. So if you take this Zwitter ion form and you put it into the gas phase, let me show you what you obtain. So this is in Zwitter ionic form. You can easily identify this as 3 hydrogens here on the nitrogen, no hydrogen on the carboxylate group. And if you look at this, this is, okay, sorry. Okay, we can look at this. This is a molecular dynamics, a quantum molecular dynamics. And you can see what happens. Yeah. You see that you have immediately a proton transfer, and that the Zwitter ionic state of glycine in the gas phase is not stable. This is a simulation of, I don't know, maybe it's a few seconds. It's super fast that you have the hydrogen transfer. See it again. Even so, it's a starting point. If you look at the starting geometry, I really did it. I really made it so difficult for the molecule because if you look here, I have basically a 90-degree angle between the oxygens and the amine. So it really needs time to rearrange. But this is at 300 Kelvin. This is not a temperature. This is at 300 Kelvin, and you see it happens immediately. And the situation is even more fundamental because if you look at gas phase optimization, then it's at 0 Kelvin, starting from the same structure. This is a starting structure here of this optimization. Yeah. You see also in the optimization immediately the hydrogen transfer. Yeah. See this? Okay, put this a little bit up here. See it. Yeah. It's immediately in. Yeah, so there's no question. The Zwitter ionic form of glycine does not exist in gas. Here's a very nice question I would ask a student if you want to make a small computational exercise. So how how much groups, CH2 groups, how much more groups you have to put here in between, then this transition does no longer happens. So can you basically block this transition by making this bridge longer and longer and longer? I really don't know. The amino acids do not become very long. So from this point of view, the amino acids and pseudoions in the gas phase will probably not exist. But if you put longer and longer, maybe at the point you can stabilize this. Yeah? So this is the gas phase. If we now go into the liquid phase, the situation really changes dramatically. And I show you this here. Okay. It's a little bit crowded, but look at the green atom. This is a nitrogen. So you see the green atom has the 3 hydrogens there on top. Yeah, so this is a Zwitter ionic form. And now we let it run. And we can also look at these here. And what you see already in the energy scale here, you don't see this abrupt jump you have seen in the gas phase. Yeah? It stays here. And you see that the Zwitter ionic form is stable. And this is a calculation where you use here a QM system. Also the glycine is QM, and everything what you have around here are molecular mechanics. So this calculation from the computational effort has an overhead to the free glycine calculation of not more than 5%. So if you can do the glycine calculation, you can do this kind of calculation in solution. So that is a big advantage of QMMM. Having said this, there is also danger. After we did this, we did this actually before of the pandemic. We started with this, and I'll show you a movie in a moment about that, which I showed at the Demon workshop. People have figured that this is really a scientific problem because they have measured glycine indeed in meteoroids. And they found, also in the ice of meteoroids, that glycine in the ice of the meteoroids is not Zwitter ionic. It's in the neutral form. And so the people now are looking at this in a much more sophisticated model, not only putting the glycine in the QM region, but also putting some waters in the QM regions. And in that moment, you can have proton transfers from the glycine to the water and over the water back to the glycine. So you can have a proton transfer to the neutral form under certain geometrical conformations of the glycine. And it is believed that these geometrical conformations of the glycine are particularly abundant in glycine meteoroids. The question is, why is this so? Now, to make it even more crazy, people in France, we have a very sophisticated real-time TDDFT. So that is where you can bombard particles with alpha particles, where you can bombard molecules with alpha particles and all that. They are now studying this under bombardment in order to see if the cosmic ray bombardment is responsible for this particular form of glycine in the meteoroids, which you do not find here on Earth. That is a factor. Maybe, however, this could be also pressure. Okay, to finish this, I show you a movie. Now I can show you the movie on the other part here, which is for us more interesting because we are not so much interested on the glycine, but our interest is actually more on the water around. And here is the one I want to show you. So what you see here is actually the work of a summer student, Irenia. She was with me for 6 weeks and she did these beautiful simulations. And what she did was, she was freezing the glycine here in its neutral form. Yeah, it can move a little bit, but she was basically not allowing that this proton is moving to the nitrogen. So she forbid the formation of the Zwitter ion. And here she has the Zwitter ion. And again, this is a QMMM simulation of our very early implementation before pandemic. And what you see here is also the surrounding, which is of interest. If you look here on the water surrounding, you see that happens a little bit, but not too much. But if you here look at the water surrounding, you see enormous rearrangements with temperature. And this, what you see here, is a visualization of solvation entropy. And that is something we are interested in. We want to calculate solvation entropy of systems, for example, in water. So to see why do we have solutions that cool down? Why do we have thermic expressions in such solutions? So that is something where we are very interested. But as I told you, the glycine story really has developed into something else now with this finding, experimental finding of glycine in meteoroids a couple of years ago. And so there are people working also on that. Okay, so with this, I'm almost at the end. And the only thing what I would like to do is advertisement. This is one of the reasons, of course, why people from Silver Staffs are going around, because we do not have, as you know, an own undergraduate program. So we rely on gifted students from universities and other institutions. And in my group, I'm inscribed in 2 programs in the chemistry department, of course, but to enter into the chemistry department, you need to know chemistry. There is no way around that. Also, I cannot convince my colleagues to apologize physicists. They will not do that. They say, no, you must know what a nucleophilic attack is and electrophilic, and when they say there's no operator, then I don't care about that, but no, that we will not make. So because of this reason, we are also assigned, or we are also involved in the nanoscience and nanotechnology program. That is an interdisciplinary program that is open really to all natural science. And it has worked very good over this program. We got some very gifted physicists and also recently a mathematician now in our group, and we are very happy about it to have such a group where we have chemists, mathematicians, physicists together. We like this very much. And these are projects that I have opened. So the first one is very fundamental development. This is fundamental development of exchange correlation functions. What I told you, the Hohenberg-Kohn theorem only tells you there's a functional relation between the energy and the density, but it doesn't tell you how this functional relation looks like. And we have started to embark in a quite ambitious derivation of ab initio functions. It's in the moment one of my PhD students is working on that, Kevin Musaido. He comes actually from Guadalajara, quite gifted guy, and he is on the exchange working, and we work there on a new expansion of density of diagonal elements. And there will be a poster assigned to this hopefully shortly. Then we have what I told you already, free energy gradients. That is our major project. And I have there 2 PhD students involved and 1 postdoc. And here's a lot of work to be done because this also involves the QMM part. And so if you know somebody, if you are interested, you are more than welcome. Please contact me, and this is something I was interested. And the last one is something quite new. We started this during the pandemic situation because we were all bored. We didn't know what to do. So we have 3 groups together, one from Canada. So that's Dennis Salahok, he is from UDM. Of course, he is now in Calgary, at the University of Calgary. So then there's Michael Lorenzo, who comes from Belo Horizonte in Brazil, and myself here from Mexico. And we started to work within an NIC initiative, Artificial Intelligence for Design. The major goal of this work is to look at global optimization. So to crack down the problem of global optimization, where we use machine learning in order to devise molecules or clusters or proteins or whatever you have, how to jump on the potential energy surface in order to find the global minimum. And this is a quite interesting project, and it's quite fruitful. I think we have 10 publications in less than a year. So that's really a lot in this area. So I have given up to cover this, but it's really quite interesting. And we are searching students, all 3 groups of that, for this work. Okay, with this I'm done. I don't know how I'm doing in time. It's okay? Okay, then I'm fine. And then I would suggest that maybe if you have some time, I can show you in private the work with the UCAM in that. And I thank you very much for your attention. It was, as usual, great fun. And I hope I have not embarrassed anyone of you. I apologize once again for that. But that's my style. Okay, thank you very much. Of course, is there questions? Yeah.
So there is any question for this workshop section? Okay. So we thank Professor Andreas for the interesting network workshop section. So now we have the break for the lunch. So I am going to announce in the Spanish.
Ok, es el launch es en el FM 6203 y todos están invitados. ¿Ve? Y regresamos a las 3.